Should figure out how to start this.
Yeah, they know. He knows.
Yeah, after your opening remarks.
So we'll get started here slowly on a cool Miami day. It's nice weather, not too hot. Thank you all for coming. Yesterday we had a good set of tutorials. I think more people are going to come in. There's also weather issues. I hope all our invited speakers are here. So on behalf of the College of Engineering, University of Miami, just wanted to welcome you. This is a very informal kind of workshop. So the intent is to interact with each other. We have a day laid out. There's also hands-on instrumentation, which several of our vendors will demonstrate and also look at some of the scientific and technical issues. And we, of course, start with some nanomaterial synthesis work that different folks will talk about. So with that, just welcome. I want to keep it informal, right? And turn it over to Sandra.
Thank you so much, Tim. So again, welcome back, everyone. So I think you have the agenda on top here. So primarily, we're going to start off today with the first session of the morning, which is nanoparticle technology synthesis, characterization, and applications. As you'll see, we have a variety of talks covering all of these areas. So we're in for quite an interesting session this morning. Just a few highlights. So one of the things is that we'll go through the talks one after the other and kind of hold questions till the end when we'll do the panel discussion together for all the speakers. So with that, we'll kind of start off with Professor Frank Scheffel from the University of Freiburg. I mean, you got introduced to him yesterday, but he's a professor in the Department of Physics at the University of Freiburg, as well as he has an appointment with the Institute or Center for Nanomaterials, or the Freiburg Center for Nanomaterials, also in Freiburg, Switzerland. So with that, Frank, I'll kind of hand it over to you.
Thank you very much. I can also move the slides, yes?
Yes.
It's a pleasure to be here. As you know, I already presented yesterday the fundamentals of light scattering and static and dynamic light scattering, which also overlapped a bit with the presentation by the Malvern people. And today I'd like to discuss, I mean, within this half hour, a few applications of static and dynamic light scattering to optical characterization of nanoparticles and related systems. So let's start. So this is not working. So let's do it like this. So we are measuring in this instrument, or other instrumentation can do similar things. You are measuring angle-dependent, time-averaged, scattered intensity or scattered flux of light. So the systems, the materials get polarized by the incident oscillating wave, and they radiate in different directions. Okay, nowadays you don't see that, but inside there's a movable detector that scan like you have seen yesterday in the animation, all the scattering angles from a few degrees to about 150 degrees. And at the same time, you can stop at a certain angle and you can look at the time variation, the fluctuations of the scattered light, which then relates to the dynamic light scattering. So both can be done in one instrument, or you can combine different instruments that can do either one of these. And I'll give you a few examples what you can do with this optical characterization method, and how you can also combine aspects of static and dynamic light scattering depending on the application that you're looking at. Okay, I just briefly remind you that in dynamic light scattering, you can extract particle size distributions. We have looked at this yesterday. So in dynamic light scattering, we have this correlation function or correlogram, which decays. So this is on a log axis in time and a linear axis here. And then you have a signal strength here, an intercept of between 0.8 and 1, and then it decays to 0. And the typical relaxation time here gives you information about the typical time it takes for a particle to diffuse under Brownian motion. And via the Stokes-Einstein relation, this gives you the particle size, which is then extracted here from such a fit to this correlogram or correlation function. And the slope here And the inversion of this function gives you the particle size distribution. If you have a monomodal size distribution, this gives you very robust results. If you have multimodal size distribution, then it gets more challenging, and there has to be a certain difference between the population size in order to be able to distinguish it with dynamic light scattering and the inversion techniques. And I already mentioned yesterday that there are improved versions of the traditional Contine approach that can help you to achieve better results, like the LS Instruments Coron algorithm that has implemented some machine learning improvements to stabilize the inversion. So one of the things you can do is not only have a certain particle size distribution that you want to derive for a system that you, let's say, synthesized, but you can also look at dynamic processes. And here are some older examples, but this remains relevant and important today. For example, if you want to look at stability, so you have a colloidal particle dispersion, and you would like, and you know it is not stable, but you want to quantify how fast aggregation happens. You can quantify that with dynamic light scattering. So here's a very nice older but pioneering study on inducing aggregation in polystyrene latex sphere suspensions by adding salt. You can also introduce that by pH or by some process that you're interested in your applications. And then you can derive aggregation rate constants from these time evolution of the hydrodynamic radius as you see here, as a function of time measured by dynamic light scattering. And with increasing salt concentration, this aggregation rate increases, and you can quantify the stability or instability and compare it, for example, to theoretical concepts like DLVO theory and the like. Another related, a very different mechanism, but using the same type of technique, is the growth of fibers. So fibrogenesis, as it is shown here. So you have a process. This is related to fiber formation in Alzheimer and other bio-relevant phenomena. So you can study the growth of fibers as a function of time. Sorry, I forgot to put the labels here. This is hydrodynamic radius in nanometers as a function of hours here. So not minutes, hours. And you see how the length of these fibers grows. And this is something you can nicely study with dynamic light scattering in order to quantify the fiber growth in these systems. Now, as we discussed yesterday, you have access, if you do both dynamic and static light scattering, you have access to the hydrodynamic radius. So this comes from the Brownian motion of the particle, and is corresponding to the relevant hard particle size. So irrespective of how your particle looks, you have an effective hard particle size, which is determined by the way it moves under Brownian motion. And you can compare that to the radius of gyration, which is related to the density distribution. So this comes from the polarizability and the scattering contrast. So you have a mass distribution. The atoms, as we have also heard yesterday, the atoms in these particles or objects, they are polarized by the incident light, and they are distributed in space. And the density may vary. If you have a hard particle, the density is constant up to the radius. If you have polymeric particles or other soft and porous particles, you might have a distribution, or if you have a polymer coil in solution, and then the radius of gyration gives you a weight averaged size of the distribution, the second moment of the density distribution. And this you can combine the measurement of the radius of gyration, which is a density distribution measurement, and the hydrodynamic radius, which gives you more or less the global size of the object, how that drags also some solvent with it. And this, for example, is very useful if you want to characterize the coil global transition, or next I will also show about polymeric microgels, which are colloidal particles that are porous. So for example, if you have a polymer that goes from a bad solvent to a good solvent, it swells. If it's collapsed in a globule, it's more like a hard sphere. So you get the relation between the hydrodynamic radius and the radius of gyration as it would be for the hard sphere. If it swells, then you have a very different hydrodynamic radius compared to the radius of gyration. And this is also an old measurement. This is known. Here you see, as a function of temperature, the particle swells. Here's the radius of the hydrodynamic radius. And here you have the corresponding curve for the radius of gyration. And here, at low temperatures, when the particles are collapsed, then you see that the radius of gyration is about 3/5 square of the hydrodynamic radius. But then if the particle swells or the polymer coil swells, then you get huge differences between the hydrodynamic radius and the radius of gyration. And this you can then use to quantify the swelling properties. I cannot delve here into polymer theory, but many of you are familiar with the swelling in a good solvent, in a theta solvent, and so on. And you can also look at different molecular weights. This is the swelling ratio. So how much more is the polymer swollen corresponding to an ideal polymer chain, which would be in a theta solvent. And here you see for large molecular weight, you get a huge overswelling relative to the neutral polymer, whereas for lower molecular weight, you get much less swelling. So this type of swelling properties of particle-like polymer coils can be quantified by a combination of static and dynamic light scattering. Now, one system that is of interest, I think also in the industrial context, as thickeners and hydrogel type of materials. There are different flavors of these particles. We have studied a lot the kind of guinea pig of physical chemists and physicists, which is the poly-NiPAM microgel. So these are thermosensitive colloids made of these NiPAM molecules that is thermosensitive, such that at higher temperatures, water becomes a bad solvent. At lower temperature, water is a good solvent, and the particle collapses around 33 degrees. So you have a cross-linked porous particle, let's say at room temperature, with about 90% water inside, and then you increase the temperature, it contracts, and you have a solid colloid which has maybe 40% water at 40 degrees, and you can cycle this back and forth. It's pretty reversible with little hysteresis, and you can think about using that for all kinds of applications, and it has been used, at least in model studies, as a carrier for drugs or flavors or perfumes, as a viscoelastic modifier, as an additive for all kinds of other engineering purposes, and also for optical properties, because this changes the optical properties of the particle from something that is almost transparent to something that scatters light quite a bit. So quantifying this microgel system is not as easy as it looks, because these particles are not homogeneous. They have these dangling ends, as it is illustrated in this cartoon, and such that you have a density profile from the inside to the outside, which is almost unavoidable due to the way these microgels are synthesized. So a popular model to describe this is when you go from the collapsed state, where you have a kind of a solid sphere. So the density as a function of the distance from the center is a step profile, like in a solid sphere. But when they swell, they acquire this kind of a density profile that often is described with this so-called fuzzy sphere model, which is nothing else than convolving this step function with a Gaussian. So you have a smearing at the interface. And how much it is smeared is quantified by a smearing parameter that comes from the Gaussian distribution, which is sigma. And this can be translated into the scattering curve, the scattering form factor, simply by multiplying the form factor. So this is for the amplitude, so you have to square this if you compare it to the intensity. This is what I showed you yesterday, is the form factor, so the shape function for a solid sphere squared, and then you multiply it with a Gaussian. So this is a relatively simple solution. You can analyze by static light scattering both the size of the microgel and how fuzzy it is, so how much the interface is smeared. And this might be not so important, not so important, but it is very important, because a lot of the properties of these colloidal suspensions are dominated by interfacial properties. So as soon as these particles start to rub each other, get in touch with an interface, or you have other constituents in the material, they will interact via the interface. So the properties of the interface are of prime importance, and this sigma quantifies the properties of the interface, and you can also have additional charges and other moieties at the interface. So here, by static light scattering, we can measure this, and what you need to have for this type of studies is a very controlled instrument. So this is a control measurement just to illustrate. If you want to do this type of measurements, you need to make sure that the scattering from a reference sample is absolutely angular independent. And this is shown here by measurements using a toluene reference sample. So this is within a fraction of a percent. And you also need very good temperature stability if you do this type of experiments. These are relatively large volumes of liquid where the sample is embedded in. So this is a precision measurement. And this makes it a bit more challenging to keep the temperature very accurate. But here we are talking about a stability of a fraction of a degree that you want to have in order to monitor this swelling and deswelling of the microgels. So here are a few scattering curves that you extract for the microgels. So here we see as a function of temperature. So here you have 10 degrees and you see nicely this dip of the shape function. And this fit here in the red line also includes the smearing exponential that comes from the Gaussian smearing of the interface. So you see you get perfect agreement. And there's an additional correction for reflection from the cell that is included here in this fit. I mean, the purpose of this plot is mainly to show you that you can get really, really very accurate and quantitative agreement between the model fit and the data. And then you extract here without going into too much details. You can get the core radius, you get the smearing parameter, you get the polydispersity, and all of this as a function of temperature. And you can run that overnight. You get all the angles, all the temperatures in one shot, and you can use that to quantify properties, for example, of these microgel suspensions. You can do even more, and this is something we are currently working on, and there's some preliminary work or previous work that has been done by others. You can also put these microgels, colloids, under osmotic pressure, and this is something that might be naturally occurring in your formulation, or we kind of here we initiate that by adding additional large molecules like PEG or dextrane that apply an osmotic pressure on the microgel. So you not only have the natural swelling of the polymer microgel in the solvent, good or bad, you have additional osmotic pressure from the outside that might modify the properties. This we can also monitor with static and dynamic light scattering. So now you have a concentration of dextrane or PEG outside, which pushes on the particle from the outside, and we can monitor the size of the particle and the deswelling or the compression of the corona, so the fuzzy interface and the core. And there is some preliminary work that has been done by the Alberto Nieves group and others, Walter Richtering, where you see here the radius now as a function of the applied external osmotic pressure. And if you study these radius versus osmotic pressure curves, you can extract the elasticity of the microgel. So how squishy it is as you apply an osmotic pressure. And this you can later use in applications where we want to look at the viscosity or the elasticity of dense microgel suspension. So there you can really get deep insight from this type of optical characterization. Another interesting and unique way of analyzing scattered data is to look not at the direct polarized component of the scatter light, but at the depolarized scattering. So what I showed you yesterday, basically you have an incident electric field that oscillates from the laser, it excites the material and it radiates. But if you have optically anisotropic, like birefringent objects, either being a particle that is birefringent or a rod-like particle, then you also get depolarized scattering. And this is very interesting in dynamic light scattering because by depolarized scattering, you can probe rotational motion. And I will give you two examples why this is relevant. So rotational motion, you get obviously, you have an interest if you have rod-like objects, but it can also be interesting if you have even spherical objects to probe the rotational part. So how does the rotational part contribute to the signal? So here you have, as I said, you have the incident oscillating wave, you have your rod-like particles or birefringent particles, and then in the scattered light, you have a polarized signal and you have a depolarized signal. So depending how strong your birefringence is or your optical anisotropy, you get more or less depolarized scattering. that is sensitive to the rotational motion. And you have to be able to separate these two. And how do you separate these two? This is a bit fast, I know, but if you're interested, I'm happy to talk about it in more detail. If you measure the diffusion coefficient of the particles from depolarized light scattering, you get a translational contribution and a rotational contribution. And the rotational contribution is not angular dependent. So what you can do is you measure the effective total diffusion coefficient due to the Brownian motion, and you extrapolate to 0 angle, and this gives you the rotational diffusion coefficient. So without going into the mathematical details, believe me, you can measure this way the rotational diffusion coefficient. And this is interesting for two reasons here that I illustrate. One is, which is discussed in this paper, if you have a very kind of messy sample, as it is often the case in a bio system, where you have all kinds of proteins and antibodies and I don't know what, and you want to look, for example, at the interaction between a nanoparticle and a specific moiety inside your mixture, then you can functionalize this nanoparticle so it binds to a certain species. But in normal light scattering, you wouldn't be able to detect that because there is so much contribution from all kinds of other particles or proteins in your system. Now, if your sensor particle, if your probe particle is optically anisotropic, which many metal nanoparticles are, then you can kind of filter out just the scattering from this particle due to the rotational diffusion, and you can really effectively probe the interaction of this functionalized particle with your biological solution. So without going into detail, this is described in this very nice paper by my colleagues in Fribourg that describe this method, which is also highly cited. And here's another example, just briefly, where our colleagues in Australia, Gary Bryant in Melbourne, they looked at rod-like particles so if you study at different angles, as I said, the correlation function or the correlogram, then you get contributions of translational diffusion and rotational diffusion. And if you extrapolate all of that to small angles, then you can extract both the hydrodynamic radius of the translational diffusion and the anisotropy due to the rotational diffusion. So all of this is well documented and can be done if you need this type of equipment where you can really change the scattering angle continuously and to lower angles. So in the last 10 minutes, 8 minutes, I want to say a few words about microrheology and viscosimetry. So we have talked about particle characterization or polymeric system characterization with static and dynamic light scattering. So in particle sizing, we have to know the viscosity of the solvent, so we can, via the Stokes-Einstein relation, extract the radius. You can also go the other direction. You can say, okay, I know the particle size because I introduce it. I introduce particles of a certain known size. Now I can extract the viscosity of the system. So this is something that also our host here, Samuel, our chair, has worked on quite a bit. You can implement that in dynamic light scattering and also in, just so 1 or 2 slides, also in what is called diffusing wave spectroscopy. And I also want to highlight why 3D dynamic light scattering, which I introduced yesterday, which is this advanced light scattering tool that we developed, is beneficial in particular for this type of applications. So as I said yesterday, and I just repeated, the Stokes-Einstein relation relates what we measure, which is the particle diffusion coefficient, to the hydrodynamic radius and the viscosity. Normally in dynamic light scattering, you extract the hydrodynamic radius, but no one prevents you from extracting the viscosity if you know the hydrodynamic radius. So this is kind of a light scattering viscosimeter, and it can be useful for some applications. For example, if you measure dense protein solutions or other antibody solutions or other biological specimen where you have very little volume available, because this can be done in really small volumes as low as 4 microliters. Now, if you do that with light scattering and your system you want to analyze is dense, and we talked already a little bit about that, your system might be already a little bit turbid or translucent. So if you have a dense protein solution or other large biological molecules or other type of macromolecules, it might not be completely transparent. So if you add the tracer particles, to a certain concentration, but you want to still stay in the single scattering regime, so you don't want to get multiple scattering contributions, then you have a mixture of signal between your matrix, where you want to determine the viscosity, and the particles you introduce that act as probes of the viscosity. And that's difficult to delineate these two, to separate these two contributions. So what you want to do in order to mask the scattering from the background is to add more tracer particles. But if you add more trace, I mean, we are still talking about relatively low concentrations, I mean, fractions of a percent. But if you add more tracer particles, then you get multiple scattering. And that's where the modulated 3D cross correlation comes in, the advanced light scattering, where you can suppress the multiple scattering. So here you see a dense protein solution, you see the protein signals, you see the particle signal, and they're kind of mixed together. Now you increase the particle concentration, then you get rid of the protein signal, because then you get dominant scattering from the particles, but you have to eliminate the multiple scattering. And then you can nicely, from this correlogram, you can nicely study the correlation function, the correlogram decay as a function of protein concentration. And from this, you can extract the viscosity. And this has been done by my colleague Anna Stratner in Lund, which you can look up here. Unfortunately, I didn't give the reference, but I can give it to you if you're interested. So this is the relative viscosity of different proteins up to very high. You see 300, 400 milligram per milliliter protein solutions, as it can be relevant for certain pharmaceutical applications. And this is fitted, I think, with an effective hard sphere model for the viscosity that you can extract in very small volumes here. And this can only be done if you suppress multiple scattering with this precision. Okay, last 2 or 3 minutes, just because I haven't talked about this at all. And this is also a method that Samuel and I and others have been working on. You can extend the dynamic light scattering to a regime where the system is extremely turbid. White, like a white emulsion, milk, very dense systems, a lot of emulsions in general are very white and cannot be accessed with traditional dynamic light scattering, even if you use the multiple scattering suppression, 3D light scattering that I introduced yesterday. So in this case, you can still do this type of analysis of the Brownian motion using what is called diffuse light scattering or diffusing wave spectroscopy. So a sample, let's say, looks like this. This is a jammed emulsion, so 60, 70% volume fraction of droplets, like mayonnaise in a jar, or like some kind of lotion. So this is white and turbid and can also be viscoelastic. And then you can still do light scattering, but now the light is scattered diffusively, like you see in this cloud here. This is symbolizing a light cloud. And you can look in transmission or in reflection how the light fluctuates, light that is coming from this light cloud inside your sample. Since I only have 3 minutes, I cannot go deeply into the theory of the scattering, but this can be done automatically using equipment that we have also developed. And then you're losing the static light scattering information, more or less. It's condensed in one parameter, which is the turbidity of your sample, but you can still analyze the mean square displacement of the particles in your I mean, in this case, the emulsion droplets, or if you add tracer particles, or if you have a colloidal suspension of the colloidal particles. So this is illustrated here. So now we have still a laser that is incident on our sample. The sample undergoes Brownian motion, and we study exactly the same thing as in dynamic light scattering, the fluctuations of the scattered light using the correlogram or the intensity correlation function. And from this, we can extract the particle mean square displacement. And we can relate this either to the radius, which is not a common application here because these are very dense systems, or we can extract via a generalized Stokes-Einstein relation the viscosity or the whole viscoelastic linear spectrum. And this is just a bit of a teaser because I'm running out of time. So with this, you can then study what is known as microrheology, which is going further than just extracting the viscosity. So you can extract the full viscoelastic spectra by converting the mean square displacement as a function of time to G prime and G double prime. And I just have 2 examples. So this is a study we did with Norbert Willenbacher in Karlsruhe in Germany. So here you see viscoelastic spectra in micellar solutions. This is the storage modulus here with the solid symbols, and the upper line here is from diffusing wave spectroscopy microbiology, and the lower symbols here, the open symbols, this is this is G double prime. So the symbols on the left are using classical rheometers like the one you will see this afternoon. And then Norbert Willenbacher, he has some special tools, piezo tools and resonant oscillators that he can go to very high frequency. This takes hours or days. And the measurements with the diffusing wave spectroscopy take like 5 minutes. So in this case, you really get, this is a model system, you get really nice agreement between the light scattering rheology and the classical rheology. This is not always as good. It depends on how well you can embed the tracer particles in the system, but it works in general and can be a useful addition to classical rheometry due to the fact that you can contain the system in a cell, you can measure it over and over again, it's sealed, there's no evaporation, there's no mechanical stress on the sample, everything is in thermodynamic equilibrium. And I just want to highlight that, as Samuel mentioned yesterday, he has worked on that during his PhD and afterwards a bit. This is a shear compliance, which you can also get from the mean square displacement for pluronic dense solutions, which are viscoelastic, and here you see for different concentrations how the shear compliance evolves with time for different concentrations that you can get from, again, diffusing wave spectroscopy, here the solid lines, and from a rheometer, the open symbols, if I'm not mistaken. Okay, with this, I'll conclude exactly on time. Thank you for your attention. If you have more questions about the method or the applications, do not hesitate to contact me in the break or over lunch. Thank you.
In business on kind of aerosol-based synthesis of nanoparticles. So I kind of hand over to Pratim.
Thank you.
There's a way. Yes, so you can do a slide, go forward, backward. I think so. Or yeah.
Good, thank you. Good morning, everyone. This session, there's a lot of different topics. I think you're already getting a good flavor as to why instrumentation is so important. I'm going to give you a little broader perspective and talk about gas phase synthesis methods. And we focus a lot on different kinds of materials, but I want to bring in some other concepts you hear in other disciplines of circularity, circular economies, sustainability. I mean, and we feel gas phase processing can bring that also to the forefront, right? By the way, gas phase processing, it's not new, as I think briefly mentioned yesterday. It's more than now 100 years, but has been done very empirically. So I'll pick on 3 materials. Fumed silica. I see one of our organizers having a cookie or something like a donut. That has a layer of fumed silica. So he's consuming fumed silica. It's produced in 500,000 tons per year, right? So all the way to consuming this nanoparticle. When you eat your cookie next time, you're also consuming some of that. The next one is carbon black. Many of you drove here or got a Uber ride. All cars still have tires, wheels. We don't change our tires so frequently as we need gasoline. Of course, now you might have an electric vehicle, but you'll still have a rubber-based tire. The rubber is strengthened by adding carbon black, also made by a gas phase process, 1.5 million tons per year, right? And then I pull up titanium dioxide, which is everywhere, paints, toothpaste, you interact, maybe it is more like 10 million tons per year. So large quantities, and these reactors are humongous, but I'm going to take a dive in. There's a lot more to do. Firstly, we should always thank our students. They do all the work. I pointed out some of the current students here, and I'm going to primarily talk about Sujit Modi's work in this presentation. But many of the others are here. Please reach out to them and they'll be happy to show you the lab and of course the funding agencies. So 3 things that I'm going to talk about in this half an hour that I have: aerosol processes, enabled synthesis, just to give you a thing that I gave you 3 examples, but what we do in our lab. We talk about functionality, the application, but how about sustainability? All right, we need to bring it to the forefront, and it is already coming up. So how do I design a process? And I'll pick a case study: lignin as a waste material, making carbon nanoparticles, quantum dot carbon particles, or carbon dot particles, carbon nanoparticles have tremendous application. Next time you watch your television set, most likely there are carbon dots in it, which make the images crisp and so forth, along with many other applications. So this you saw yesterday in those who attended the tutorial. We try to understand this, and and now I'm applying it to the synthesis, right? So I can do fundamental studies. I'll allude to it. And then, of course, applications also I'll allude to. In the 30 minutes, we go through quickly. And each of these steps, if you develop a good understanding, you could then develop processes. And I'll also bring instrumentation to bear here. So this is a fascinating field. You know, it has applications, of course, in environmental issues, but we talk about health effects, but more so in resolving the health effects by producing medicines for cancer treatment, delivery using respiratory routes, energy field, agriculture, and large commodity powders, okay? So many, many applications can be dreamt of. So they allow controlled synthesis. By understanding each of those, I can tune my reactors to control it. So I can control the size, the shape, and the composition. We have aerosol instruments, which could be real time, at least in the laboratory. In an industrial reactor, we have to deal with much higher concentrations, and some of these may not work out well, or we need dilution systems, but the ability to measure things in real time bring another tool to the forefront, which allows us to develop these processes. And ultimately, the properties of the material, the crystal structure, even the orientation of the crystals, depositing thin films, these all become, or these enable applications. There's a good review article that we did with some colleagues a few years ago, but it really is a good compilation for those who are interested. I mentioned measurements. It really is an enabler, and also simulations. Okay, so let's talk about it. I'll show you pictures. You can go a few floors up and you might see some of these, or the students who are here can show you around. So this is a simple flame reactor. It's in some sense controlled, but I could produce, you know, gram quantities per hour in such systems. And some of these reactors could be turbulent flow reactors. You basically have a fuel or a precursor that combusts, and then you dilute and capture this. The thing on the top will actually capture your nanomaterials. And there's a lot of control systems. You want, here you can see the different capture units, the structure of the burner, and all the control systems and so forth that go into play. Then we have simple furnace reactors. Instead of a flame, I might want to control the temperature. So this is externally heated. And instead of a flame, I have a furnace. And in that, I have my reactor. And then, of course, I might want low temperature processes. I want to use charge on particles. So there are electrospray generators where I can do low temperature synthesis, or I could use these as delivery age devices and so forth. And finally, this again are pictures repeated, different applications and making all kinds of materials. I think you'll hear some about plasma reactors later. We also did some work. Plasma can be used to enhance charging for processing materials along with flame and furnace. So the reason why we go to these high temperatures, recall again, I want to go into a molecular state, and then I want to put the molecules together to make my functional nanomaterial, right? Or my designer nanoparticle in some sense. And high temperatures in the chemical industry will also enhance kinetics, because ultimately we want to scale these up. So we want these gas phase processes or utilize the advantages. And then I can start listing, even in our lab over the years, make metals, metal oxides, carbon, soft materials, composites, all kinds of stuff, composite nutrients for agriculture, for drug delivery, cancer treatment, detection. It's really a gold mine, right? So we can do so many different things. And I just categorize here into different categories. Again, energy storage applications, photovoltaic systems, nanoparticle delivery, and so forth, right? So let's move on. The next thing is I can get the functionality, but how about sustainability, right? Can I bring that to bear? Of course, change in administration now, you might not hear this word, but this is an economic driver. So chemical industry is going to love it, will continue using it. They might use certain other terminology. So I want to bring that to bear. So is functionality enough? And I would say no. In fact, the industry is already realizing this. Understanding the fundamentals allows me to do all the things I talked about, and can get desired materials for applications. But an important consideration is that of sustainability. And obviously, you want to ensure that you don't have an environmental footprint, right? And this will only happen with a holistic analysis. Like we talk about electric vehicles, and people talk about life cycle analysis. Is that better than a gasoline-fired vehicle or a conventional automobile? And sometimes people begin to question these things. So a holistic analysis is needed, especially if we are going to talk about scaling up. And we face these global challenges, climate impact, pandemic. So this is all related to sustainability. And that's what I want to bring to the forefront, and even challenge advanced materials researchers to take this into account. So I want to start with certain precursors, want to make an advanced material or a commodity material, but then keep this as a factor in mind, and a holistic analysis. And there are tools now, at least used in many other fields, especially in the environmental field. You bring in economy, there's always societal impacts, there's the environment, there's supply chain. We talk about electric vehicles, where will the battery materials come from? And we also have colleagues here working on some of these in great detail, or folks in the business school who work on supply chain issues. But I'm just trying to integrate all of this into the material synthesis issue. And we hear a lot about carbon footprint, while we don't do that much here, but the industry is really now tuning up to this. Of course, in Europe and other parts of the world, there are also financial benefits to this. But if you look at the carbon footprint, this is a real issue. And in Miami, we face this. People are all believers here, surprisingly. In Florida, people believe in climate-related issues because they see the sea level rise. But advanced materials, functional materials, commodity chemicals contribute not as much as energy production, but also contribute. Agriculture, it's basically through the use of materials and so forth, fertilizers, pesticides. Cement is another good example. A lot of high-rise buildings, cement has a very large carbon footprint if I look at the material sector. So this also has an impact to play, right? So the remainder of the time, I'll just do a simple case study. Of course, go into the lab, and from lignin, and I'll tell you what lignin or where it comes from. So let's look at carbon-based products. Again, rethinking how we can make them. And we always think we are smart. We are one of the first who want to bring this in, but people have been talking about it. I mentioned carbon black, right? Carbon black is made from petrochemical waste. The petrochemical processes that are used to pull out the gasoline fractions and of course sell to you with at a high price ends up with a waste which is then taken up by companies to make additives like carbon black, which is added to rubber, which makes your tire so strong, right? And you don't have to change it every time you go for a gas tank fill up. Carbon dots, forget tires, right? You'll think, oh, that's a routine application. By the way, there's another problem with carbon black. When you're driving your car around, you're sloughing off these particles, and that causes other exposure issues, especially in high traffic regions. So there's a lot of work still to be done, and people are looking at alternatives. And you might not love the color black, you might want a pink tire, and then you want to make a nanoparticle which will strengthen your rubber and give you a pink tire. People are actually working on these things. It's another talk. But carbon dots, quantum carbon dots are used in high-level applications, advanced applications like electronic devices, television sets, biological sensing, drug delivery, and so forth, right? So people are now using all kinds of techniques to make these materials, very high cost. So if you go to the market and want to purchase these are high-value materials. A small amount is used, but it's very expensive on a per unit mass basis. People are using top-down, energy-intensive, corrosive chemistry pathways to make them, but the bottom-up approach, which I call the gas phase synthesis, can really become better, can be more sustainable for this synthesis method, right? And then ultimately, carbon biomass is the biggest source for carbon. Biomass is carbon neutral. If that is one of the things, people are using wheat, rice straw, coconut shells, waste, and that's what I'm going to focus on in my case study. So we start with trees. We get the carbon-based material. I can see paper on, if not paper that you're writing on, people now use laptops, but the tissue that you're using or the paper is not going to disappear. It comes from trees. But when you pull out the paper, you end up with a large amount of waste byproduct, which is lignin. And the amount of lignin, it is in some sense low cost. The valuable material might be pulled out to make paper or other components from biomass sources. And then the waste is actually just burnt, right? They make fire logs. And of course, on a cold wintry day, fire logs are great. But could I make higher value materials, right? So people are now trying to take the lignin, valorize it, use wet and batch techniques to make all kinds of valuable materials. And just look at it, from all the way from porous carbon nanoparticles to materials for batteries, for agriculture, for drug delivery. People are beginning to use these materials. So it's not new. People are doing a lot of things, but they have limited property control. Harsh chemicals have to be used. It's batch processing technique. So I want to bring gas phase processing or alternate methods of processing. And this is where our tools could help, right? So I also want to do it in a single step and in a continuous process. So I start with a precursor, which may be water soluble. I would want to use aqueous solvents and then aerosolize it, then dry the droplet, and then do pyrolysis, maybe in a heated reactor, collect the particles. This is a simple setup in the laboratory that we can put together and look at the different things. But there's a lot of different processes. There's a chemical transformation. If I want to go from lignin, which is a complex organic molecule, and even a type of a polymer, to all the way to carbon, I have to pyrolyze it. I have to go through some chemical transformation. Then there is a physical transformation. The advantageous properties might come if I can make a porous material, and I want to create a porous structure. I want to create nanoparticles of a certain size. So there's both chemical and physical transformation. So these are all the systems that I have to study, and I want to bring instrumentation in, and I'll just highlight in the remainder of the time how we do these studies. So I can put the process together. So I start with a simple evaporation technique, droplet creation by nebulization, atomization, spray techniques. If the temperature is low, on the top, I'm just going to dry it out. That's a spray drying process, very conventionally used at scale. I might have collisional growth, but I get lignin nanoparticles depending on the initial concentration I use. As I elevate the temperature, some pyrolysis takes place. Certain vapors will be released from these lignin particles, and then I could have all these aerosol processes that I talked about. And if I heat it up even further, maybe some of these processes dominate and I can get different structures. The residence time can be controlled. I briefly alluded to characteristic times, and even doing this kind of an analysis, we can begin to design reactors. And you see that you get particles which look very nice and dandy. The structure changes from a simple nanoparticle to a more porous structure, high surface area, smaller mean size, and we can do all these different production methods, right? Just by controlling the processing conditions, because we understand the different pathways. So if I look at the BET surface area, it's an instrument. This is offline. I produce the particles and I measure the surface area. If I synthesize at different temperatures, I can increase the surface area per unit mass as the temperature goes up. And same way, if I keep the temperature constant and increase the residence time, more pyrolysis takes place, and I can also enhance the surface area, right? So these are extremely high surface area carbon nanoparticles, and there's tremendous demand for such materials in the industry or for different commodity production. So, but I really want to scale this up, right? So there are continuous pyrolysis reactors being designed, but some of these processes go off target. For example, sintering might begin to dominate at the elevated temperatures, and then they might even plug up the reactors and so forth. So we really need a deeper understanding. This is where the fundamental study of like sintering, particle formation, sintering, and chemical reaction needs to be understood. Now, sintering has been studied in our community very extensively, but sintering concurrently with reaction, with pyrolysis has not been, right? So we need to do some simple modifications and develop models to do that. So again, so we develop a model accounting for all these steps. Ultimately, I want the size, the shape, the surface area, the chemical structure. And just to show you, I start with a certain distribution of lignin droplets. As chemical reaction takes place, the distribution shifts to the left, which means I'm losing mass from the particles. And I'm plotting it with particle mobility size. I'm going to bring certain instruments that hopefully you'll get to see later on. I know folks from TSI are here. I'll also illustrate how we can use these. The particle, then as collisional growth takes place, the particle distribution shifts again to the right, which means due to collisions, particles are sticking together and becoming larger. The concentration is decreasing, number concentration. And then sintering takes place, and I have maybe a reduction or a shift to the left again because of a surface area collapse. We tend to move towards a spherical structure. All of this I can put in an equation form. I won't go into the details. We put all the terms in and we have to study it. But I want to just highlight the role of sintering and chemical reactions because that's a new contribution that the student has developed these relationships. Sintering is when two particles that are sticking together begin to coalesce and form a single nice spherical structure. There's a driving force towards that. But simultaneously, we are losing mass. So we need to simultaneously study these processes. Because it's not a spherical particle, I just can't use particle volume or particles size to describe it. I need to also account for the surface area. So the combination of the size and the surface area, and these change, like you look at the first equation, by collisional growth, the size of a particle increases. That's the first term. By chemical reaction, that's a reaction rate, the size shrinks. By nucleation, I will form new particles. The size tends to again create new particles. So there's an increase in particle size. And the last term is condensational growth. So we account for all terms. Same way in the surface area, when I have collisional processes, the area increases. Sintering will reduce the area. Reaction will reduce the area, and condensation increases the area, nucleation increases the area. So there are different characteristic times. We need to put all of these together. Of course, there's a lot of detail here. And you can then experimentally, you want to find out some of these constants, right? This is where a fundamental study allows us. And this device, it's a scanning mobility particle sizer. I can use it in a mode, in a differential mobility analyzer mode, where I can sort of classify the lignin droplets coming in to be monodisperse or close to monodisperse, which means same size. So I send in all particles of the same size, and I study the chemical reaction or decomposition by measuring the new size again at the outlet of the instrument, all in real time. And I can get a plot of volume of particle as a function of time with temperature, right? So this would give me an analysis. I make a plot, and it's a Arrhenius type plot. I can get the rate of pyrolysis by just fitting the data at different temperatures and so forth, and come up with the activation energy and things like that. So all done experimentally, of course, plugged to the simple theoretical expressions. I similarly want to study sintering. And here, again, I use my mobility sizer, but now I'm trying to send in agglomerates, right, initially, of these droplets. So there is a chamber, a pre-chamber, we call it a collision chamber, which allows me to generate those agglomerates, soft agglomerates, and then study these processes. So now pyrolysis is taking place with all the aerosol dynamic processes that I talked about. And the surface area, again, now decreases as sintering would take place at different temperatures. There are, again, equations, but remember, I have to understand the chemical reactions here too, because that's also going to change the surface area. I combine all of that, and I can pull out a sintering coefficient or a characteristic time for sintering. And all of this then very quickly now could be put into reactor scale models, where we can have a plot, a plot which gives me a residence time versus temperature plot, depending on what I want to do. So for example, if we want a fixed temperature and I want to enhance sintering and go towards more spherical structures, I can do that. So you can see that negligible sintering, I'll get agglomerates, partial sintering, complete sintering, and so forth, right? So this is a map which allows me to now do different things. So if I'm making an antioxidant or a UV protectant, right, like a sort of sunblock, I might want an agglomerated structure, and I will then choose my reactor conditions. On the other hand, if I want to make a battery material or a supercapacitor, I want a completely sintered material and so forth. There are some sintering theories here that we have very elegantly derived. I'm not getting into it, but just to show you, functionality still matters, and some of these could be tuned to enhance the functionality. A lot of detail. This is cyclic voltammetry for a material that is used in a supercapacitor. And you, of course, want to, get a good functional material. And it's related to the surface area. The specific capacitance goes up as a function of the surface area, and you can choose your conditions and so forth, right? So the last thing I want to touch upon very quickly is the life cycle analysis. This is great, but what happened to all my sustainability things? So there is a metric called the global warming potential that people are using. So I want to bring that to play. And very quickly, there are tools for life cycle analysis. That's just a standard software that you could use. It's basically a mass and energy balance. So I want to do that for my lab scale reactor, but I want to scale this up, right? While I won't do it in the lab, scale up techniques are available. You know, chemical industry has all these unit processes. I can then also derive it. I can come up with configurations. I might want to recirculate some of the gas because it's heated up. And we put all of this together, and you see all these parameters are popping up and do a very detailed analysis. Ultimately, I want to look at the carbon footprint per unit mass of carbon material produced. So you see the batch processes have a very high carbon footprint, whereas some of these aerosol techniques have very low carbon footprint, right? So the global warming potential is really advantageous, and some of it is coming because I'm using a waste material. And then I could also look at the carbon footprint per unit performance characteristics. I might not care for the amount of material, but I want functional materials. Again, here, in fact, the aerosol process works much better compared to batch processes. And eventually I can compare different kinds of carbon materials and again, look for these techniques. Graphene is another wonder material. So this has been a very nice forte into this domain of looking at this. So I'll just summarize now. This is the process I sent. So instead of burning materials, really we want to use valorization. That's just a technical term. Use a single step process to make all these fabulous materials, and these are actual electron micrographs. We can also create composites, but I do want to point out right now, if you go to the beaches, some of you will go to South Beach, you might see a lot of algae floating there. People are saying, I need to clean out the algae so all my visitors have a good time on South Beach or any other beach. And that sargassum is a type of algae that is being created in large amounts. Instead of just taking it and dumping it, this becomes my carbon source, right? So we are doing experiments upstairs where I can take sargassum and produce a very high value material, which will go into your television sets. Nothing as good as that. Easily said, but all these steps, but also very feasible. PFAS is another one. If you're in Florida, we have contaminated all our soil because of extensive use of this very inert material. And now we have to clean up our soil. People are talking of digging it up and incinerating it, a very good method to destroy it. But can I use this as a precursor, pyrolyze it? In fact, the destruction method is by pyrolysis and combustion, but now produce an intermediate material, and it's very feasible. So just from these wastes, which are problematic, we can produce a lot of these materials. So thank you for your attention. And I think we can take questions later on, right? I think I'm exactly when it's
So what we do is we'll take a 5-minute break and then kind of there's more coffee outside as well. So then we'll come back in about 5 minutes at 10:05 and get to the rest of the three talks. Yes.
I have two videos that they don't have in my slide. I don't know why. One of them runs, the other one doesn't.
Let me see. It's not working. What happened? Yeah. No.
But I'll have to. Yeah. Yes. Oh, yeah. So it doesn't work like this. Oh, it was very. No, like this. How far can you go? No, kind of go further. It was working fine. So now it stops now, right? So maybe just put it about. Put it here. Yeah. Why don't you put it here? Then that'll be okay. Okay. Right, okay. I'll be around if you have any questions.
I'll be here for most of the morning and then of course, we'll have it right.
Okay, likewise, and, you have the opportunity.
Yes, I'm gonna try to come back.
Okay. Thank you. Working.
It's not working from here, Lights are not changing. Neither of them. Yeah. That's my. That's what I'm saying, the temperature is. No, not the mount, but the keyboard. Oh, yeah. You know, it's fun. Okay, so I think we are back, from the break.
Where is my slide?
Can we just do it there or the keyboard or the mic or for the?
Connection problem.
This
So
one.
what are we waiting?
Waiting
someone-
for Frankie. to
Frankie,
figure
okay.
out. Yes.
Because I know the team has to leave at 11.
Yeah.
So we just need this Q&A with the main meeting. Yes, to leave. So if we delay like this.
Yeah, might as well, yeah. Yeah, yeah, yeah.
We are having a little bit of a, excuse me, I'm really sorry, but we are having a little bit of a technical difficulty here in getting the site to move on. So we are waiting for the IT person to come. In the meantime, I think what we can do is, instead of wasting this time, the first two speakers or Professor Vishwas can come here and take the Q&A. Yeah, because I know. Yeah. So let's do that. I think Professor Vishwas, you might want to come and take the Q&A and, yeah. Okay. So, welcome the panelists. We are doing it in 2 steps now. The panel session. Let's do that. Question answers please from the audience. So questions for our first 2 speakers. So maybe I can start out then. So I mean, in terms of one of the areas for particles, obviously is in the consumer world, and there basically sustainability is a big driver. So 2 questions on that. One is basically what is the, I saw the mean of 60 nanometers. With consumer world, they're always a little bit wary of anything below 100 nanometers. So kind of what is the upper limit that we can kind of push these sizes to?
Yeah, the larger particles are easier to synthesize.
Okay.
I was focusing on the very advanced applications of quantum dots. When you look at consumer products, so larger particles are in essence, easier to synthesize.
Okay.
And much more cost-effective manner. But ultimately, even these nanomaterials that are produced, they go into a matrix. So there's, of course, like even the supercapacitor is actually a film. It's on a matrix. It's immobilized in that sense.
Right.
So people, but if you talk about agriculture, same way. If I say it's a nano fertilizer, there'll be a lot of panic. The exposure will, some unwarranted, but some warranted. So there again, you're creating a composite with nano constant.
Right, that's
So
what
the final size is much larger in terms of what, when it's seeing the consumer or in the product.
Right. And the other second kind of related question, you talk about functionality. I mean, in terms of when we kind of think about functionality of particles in the, again, in the consumer or even in the bio-related world, one of the things which is important is trying to drive amphiphilicity into the particles. So is it possible to kind of create almost like amphiphilic particles where kind of you have hydrophobic modification on one end of it?
Yeah, so of course I didn't talk about it.
Right.
I just focused on a simple LinkedIn application for supercapacitor. Yeah, so you could do coatings. You could also use, there are certain types of lipids that people use, control, or you could get constituents. One end of which is hydrophilic, the other is hydrophobic. You can then decorate it and so on.
Okay.
Yeah, aerosol processing allows several methods. That's where the detailed dive is very essential. Some of it we do empirically and then understand the scale of the process. But
just to continue, so you can put any function group later on, or you in the process
you can do, so when we do drug delivery, for example, like let's say cancer, you want to target the tube, right? You don't want it to go all over the vascular system in the body. So you would put a certain functional group or antigen that is very specific to the tube, right? So it will then go and attach to the tube preferentially, right? And you get localized. But in addition, you want to carry the drug molecule. So that could be like doxorubicin is one very commonly used cancer treatment drug. So you want to decorate it. So you need like 3 components of that same particle. Okay. Test on mice and so forth.
Prashant, I have a question on if you are looking at spherical particles, but for example, if I have an agglomerate of the particle, in terms of now in particle, not in which case, is there a way from your radius of gyration, from your hydrodynamic radius, you can calculate that, and but can also the fact that when you have a an aggregate structure, then when you have the bombardment of molecules, they can have a specular reflection, or they can have, they can have multiple reflections because they can bounce back and forth between the, it's a tree, like throwing a ball into a tree, right? And that will change its, I'm guessing its diffusional properties and the Brownian motion and everything. So is there a way to extract from all this information the fractal dimension of these fractal particles from your?
Many questions condensed in one, in the sense, I mean, in principle, yes, I mean, people are, you can study fractal dimension from static light spectrum, aggregates, for example, nanoparticles. You don't get this information from the higher level, so you have to do a static light spectrum, and the aggregate has to be very high. Or space for the then you get a power law depending on the fractal dimension, and then you get with low Q, you get the total size. And combine it with the real and light. Aggregates are fully floating. You have a lot of polydispersity and yeah, but for your I want to in the last presentation, you mentioned that you use GitHub, you know, for something. So, I think we also should have a very important player at the list. So, concentration is high goal. I mean, concentration like GitHub, water, high flow, water in the flow. So, how to collect material?
Yeah, that's a good point that you talk about weight, but in this case, it's a soil matrix, so it's quite concentrated, so because they have probably been done from use. So you can dig up the soil. It's soil matrix with that's out of the soil matrix and then so, but you're right, it will still be a dilute system, complex system with other things. So when you want to reduce it, look at it more carefully, right? But soil, it's a little more. Do you remember the concentration of PFAS in soil? I think you can be here, nanogram per gram. But it's still small. But maybe water is more challenging. Water is very challenging. PFAS is also used for firefighting, correct? So both regions is quite concentrated.
Yeah, so I have a question for Dr. Shepherd. So talk about the high scattering. I'm not sure if you have experience with gapping aerosol systems. What applications do you see? Instrumentation that I showed, you cannot use in the space. The method itself, that is not scattering, what you do it with. Sites assume that it's not so relevant. Outside is then like so it can be like the public interest or personal. Other question. How do people can the foresights?
Here, of course, we need to backward sense to be on it, so pyrolyze it, so clearly it's a, so the model is really giving that, so it is a function of temperature, residence time, sintering rates and so forth, right? So we, of course, we can empirically get the relationship and get all these parameters in the model, and then we can compare. So in large scale reactors, they have plugging issues. Thinkers partially. So there you really want to use it to control the signal. So then if you're asking, can you control the signal? Yeah.
I have a question for Dr. So I know you, both from your workshop presentations, posted a lot of difference. there are multiple detector units available in the market. So the newest ones are like more quantum scale, like they also use space-based applications. And then the older ones like CCD. So light scattering detection, what type of sense detectors would you like?
I mean, you have to distinguish between camera detectors and single photon detectors. So what I presented mostly was based on single photon detectors, and I think the statement here cheaper and better, over the last years, and we usually use two, and so you can go for Now, if you talk about plate sensors, which we also use, that's the same. Or it depends on whether you want to optimize for speed or you want to optimize for noise. The MCTV detectors that we also use for very high resolution applications, if you want to have a trade-off between speed and cost, then and there are also very new detectors which are going to be out of scope with mapping wireless very, very high bandwidth, very low noise, and we can go to very high contrast. That's often a problem with camera. The dynamic range of camera is quite limited. 1.5 to 2 hours. What we can't do the problem, but there are a lot of solutions in the market. Details of several months, I guess we'll show you some of our gas-based systems. We use detectors. We are back on track. The problem has been solved, so maybe we will resume the talk. Thank you very much. Thank you so much again. Okay, so our next speaker is Dr. Sung-Yun Jung. She's an assistant professor of engineering, School of Software Infrastructure and Environment at the University of Florida. And her topic today is on microplastic detection and analysis.
I may gesture like that for next.
Yeah, so you can just talk with Jiayu.
Yeah, yes, okay. Yeah, if you don't mind, could you go back to the first? Yes. Good morning, everyone. My name is Sung-Yun Jung. I'm an assistant professor at the University of Florida. And I'm really happy to be here again for presenting my work this year, and especially right after my PhD advisor, Dr. Biswas. And my presentation title is Microplastic Detection and Analysis, although our session title includes nano. So nanoplastic is really emerging topic, but it's challenging. So after I joined at UF in 2023, my group first focused on microplastic detection and analysis, and I would like to present some of our results today. Yeah. Next slide, please. Oh. So plastics are everywhere. Plastic. And do you know this water bottle has 2 different types of plastics? This one PET, this one PP. So there are a bunch of plastics here. Even this room, we have a lot of plastics. So plastics are everywhere, and then they have become essential for human life with extensive use in the consumer product. And those plastics can be waste, and those waste can break down due to different environmental factors such as UV radiation and weathering to form smaller particles. And microplastics are generally considered to have their sizes between 5 millimeter and 1 micrometer. And many recent studies have reported the existence of microplastics in different environmental media, aquatic species, and even humans. So this is really important to understand, but still we don't know it's really harmful or not. So there are studies are required. And of course, even though there are many studies going on, still research gaps remained. And I will explain that in later slide. let's go, yeah. But I would like to briefly explain the collection and analysis procedure first. So those processes include 3 different steps. The first step is collection of samples. So there are the different types of samples available. The first image show the air sample by using active sampler. And the second and third images show the surface soil and water samples. And of course, this is the plastic. So we cannot use plastic bottle. So people are using glass bottles and they also cover with aluminum foils. And once we have these samples, then we carry those samples to our lab for further pretreatment and the analysis. Yes. So the second step is pretreatment of samples, which generally contain 2 different steps, extraction and digestion. So for the extraction, people are using density separation method because plastics are lighter than environmental medium. So people are using different chemicals which have those densities to separate plastics from environmental media. And then those separate microplastics, of course, they have other dirty stuff, organic matter. So we have to use another chemicals to get rid of organic matter. And then we can mainly have plastics for further analysis. Let's go to next slide. Yes. So the last step is identification and quantification of microplastics. And there are different advanced analytical instruments have been used. And the first category is non-destructive method. By using kind of Raman and FTIR, they can do the chemical composition analysis. They are non-destructive, so which means we can retrieve the sample after the analysis. So that's good. But that also have limitation because it has size detection limitation. So it cannot go down around 1 micrometer over a certain micrometer, and nanoplastic is not available using those techniques. And the second one is thermal analysis. People use thermal analysis to destruct the sample to create different gaseous product. So it has the limitation because we cannot get the sample back after the analysis. And also we can use SEM or TEM to visualize the microplastics and also do some elementary analysis. So those are the analytical method, and I heavily use pyrolysis GCMS. So before going to my result or research gap, I would like to explain the pyrolysis GCMS a little bit. Next slide, please. Yeah, so pyrolysis GCMS include 3 different parts. The first part is pyrolyzer, which is highlighted in the yellow and red color. So we can load samples in this really tiny small sample cup. The size is really this much small. And then we heat the sample cup to create the gaseous product. And then those gaseous products can be then transferred to the gas chromatography. And they can be separated because of their affinity toward the column material. So that's why they can have different retention time. And then they go to the mass spectrometry for the identification. So this is brief principle for the pyrolysis GCMS. And by using this technique, we can identify and also quantify plastic types. So let's go to, yes. So as I mentioned, there are research gaps. And many people and I also agree there are 2 major research gaps. The first one is limited data sets. So to develop accurate risk assessment or exposure assessment, we have to have enough data sets, but it's still limited. And the second research gap is a lack of standardized method, although people are using really different the methodology for the identification and quantification. So after I joining the UF in 2023, my group focusing on 2 different parts. The first one, detection of microplastic in Gainesville. So we collected the different types of environmental samples in Gainesville. And then the second part is development of standardized method or any method. So in the following slides, I will show you some examples for each part. And this is the first example for the part 1, which is microplastic generated by 3D printing. So our objective was to investigate the presence of microplastics in the 3D printing laboratories. At UF, there are 3 3D printing laboratories, and we collected samples from 2 laboratories. And here I will show you some results from one of them. So if you don't mind, can you go back to? As you can see from here, the laboratory has that configuration, and we placed clean beaker in 6 different locations. And as you can see from here, there are a bunch of, the 3D printers inside the box. And the red colors box has filters, which I don't know the details because I was not provided. And the blue ones, they don't have filters. So we collected the sample inside the box and outside the box, and also placed different locations to see the microplastic can be transported throughout the laboratory. Next, please. Yes. And then here after we collected the sample, of course, we carried them to the lab, and then we visualized the sample by using microscope, and we found different images from different locations. And then our interest is, yes, click. Yeah. So we found black particles, which is especially from the sample 1, which is placed in the 3D printer box, which means generally the particles probably from the 3D printer process. And then we found those black particles are also observed from different locations as well. And then our question is, what is this black particles and how much black particles are in the lab? So next slide, please. And then we use PyTorch GCMS for the identification and quantification. And we found that that particles are, can you click the slide? Yes. The polymethyl methacrylate, PMMA, because there is a distinct peak related to the PMMA. And this PMMA is, click once again, is for the different plastic application, as you can see from this image. And also it is known for the, click once again, yeah, so 3D printer filament. So we can conclude that these black particles are from the 3D printing process, especially from the filament. Click one more, please. Yes, and we quantified the amount of this PMMA particle throughout the laboratory, and we found that, of course, there are different concentrations, but still everywhere we can find the black particles and certain amount of particles, and we can say 3D printer created microplastic, and they are exposed to the people in the laboratory. Next slide, please. And the next example is for the development of methods. And our objective was to propose a new method for the efficient extraction of microplastics. You might remember from my previous slide. So pre-treatment of samples include 2 different steps. One is extraction and the other is digestion. And extraction is to separate the microplastics from the environmental media. And this first table shows the different types of plastics. Polystyrene can be found from styrofoam, and polypropylene, as I mentioned, from the water bottle cap. So there are different types of plastics, and they have different densities. And people are using the chemicals shown in the second table, and those chemicals have also different density. Click on. So which means it may be possible not to extract entirely from the environmental media by using different chemicals. And it is also unavoidable to have complex microplastics in the environment. So it is important to extract the entire microplastics from the sample. And here is our strategy. The first one, single extraction method, is heavily and widely used method by people. And they are using just one single method using a single chemical. And the second method is which we have been using for this study, which is the sequential extraction method. So we are using 2 different steps. The first step, we are using lighter chemicals to extract lighter plastics. And the second step, we use denser chemicals to extract the heavier plastics or remainder of the lighter plastics. And we found that, click one more, please. The water and stability shows the highest efficiency for the extraction of microplastic. And we validated this method for real environmental samples. Next slide, please. Yes. We collected 4 samples from the same location in Waste Collection Center in Gainesville. Waste Collection Center in Gainesville has a facility to treat the plastics. So there are a lot of plastics, and we assume that there might be microplastics near the environment. So we collected the surface soil for the analysis from the same location. And as I mentioned, we used 2 different methods for the comparison. One is a sequential method and the other one is single. And as you can see from this first the data. Sequential method shows a higher efficiency compared to the single method. So we can extract the more plastics, we can say efficiently. And then so it proved that our method is more efficient. And we also evaluated the chemical composition and those 4 pie charts for the 4 different samples. And we found that the lighter plastics such as PSP, PP are major types of plastics in those samples. And there are also denser plastics as well. Next slide, please. And as I mentioned, this sequential method has 2 different steps. So we also analyzed the samples per different steps. The first step, we use water for the extraction, so it can extract the lighter plastics such as PSP, PP. And the second step, we use the denser chemicals, so we can also extract the denser plastic and also lighter plastic as well. And those 3 chromatography shows the examples how we can identify plastics and some images from the microscope to show the real microplastic from the environment. And those are the examples. And by the way, I showed the images which has pretty high, larger size, but we analyzed the particles sizing between 1 micrometer and 2 millimeter. So there are also small particles as well. So we concluded that our new method is more efficient compared to the generally used method. And then the next slide, please. So this is the overall conclusion for today's presentation. First, microplastics are really present in the environment. And second, so we developed some new method which is more efficient, which means different methods should be compared, and we have to develop a standardized method. And then finally, we can develop an accurate exposure assessment and a risk assessment for understanding the effect of microplastics on human body. So thank you for your listening. And I really appreciate my graduate students and undergraduate students for their hard work. And I will be happy to take any questions during the Q&A session.
So our next speaker is the co-chair for this session, Dr. Devyendra Mukherjee, who is an associate professor of chemical and environmental engineering department here at the University of Miami. His talk is titled Composite and Metastable Metal Ceramic Nanoparticles Synthesized as Advanced Energetic Materials via Laser Ablation Synthesis and Solution. So thank you.
Thank you.
Thank you for the introduction. Yes, so I changed the title a little bit, basically saying what composite and metastable nanomaterials didn't want to make it so specific. I think for engineering applications, nanomaterials have been used, metalloid nanoparticles have been used like boron. There have been nanoaluminum, nanoboron, carbon nanotubes that are used for solid propellants and explosive applications. Now, the properties of the large surface to volume ratio, which you already know, the smaller diffusion length scales leading to enhanced diffusion rates and the excess free energy of the surface atoms. So that reduces the activation energy barrier for reactions on these surfaces and produces enhanced interfacial reactivity, which can be a great application for various jet propulsion solid fuels. So the first generation aluminum nanoparticles were the thermites. You take the thermites, the classic old thermite reaction, and you scale it down to nanoscale, right? And of course, due to this enhanced reactivity, people have shown the nanoaluminum, iron oxide, copper oxide, nanoaluminum, and such thermite reactions have shown very high energy reactions, oxidation. Now, the oxidation enthalpy or maximum combustion enthalpy of aluminum, compared to TNT, it's huge. So, and yet, and then you also carry to that, if you go down on particle sizes, you increase the burn rate exponentially when you go below like about 10, 20 nanometers. So the expected thing was that such reactions would be of tremendous value for solid propellants as additives in solid propellants, but that didn't materialize. Next, please. The reason was that when I was initially doing gas phase laser ablation, we made these aluminum nanoparticles which had all these oxide shells on them. So that causes the diffusion limited oxidation. the unwanted oxide shell formation, which is like a parasitic shell on it, and then there was a surface area loss. So they never lived up to the promise of the solid propellants that they were supposed to. Next, please. So to address this issue, that gas phase laser ablation basically gave rise to this idea during my PhD a long time back that why not do the entire plasma instead of a gas phase laser ablation, do it inside a liquid. Next, please. So you have its high energy pulse laser that hits a metal target, causes a plasma plume, which creates a shock wave, which creates a cavitation bubble. The nanoparticles, the seeding or sacrificial nanoparticles from the metal ablation are nucleated inside the cavitation bubble. Next, please. They come in contact with the solution, which has secondary chemicals as per our choice of chemical reactions at the bubble, the cavitation bubble liquid interface. And we can create, next please, a bunch of various composites, nanoalloys, and core shell nanoparticles. So we have patented this technique to develop a wide range of, next please, materials due to this interaction between laser ablation synthesis and the actually, yes. I didn't know that I couldn't do it myself. I think that's fine. I can do it there. No problem.
But the thing is,
All the content.
so you probably have to-
Okay, no problem, no problem. Let's go on with whatever it is. So, wide range of materials being made for electrocatalytic battery and supercapacitive applications that we have applied this technique. So we have proven the versatility of the technique. But today's talk will be on energetic nanomaterials, right? So next, please. So, with that, we will talk about the, that's fine, which is, those are the work we've done before. So, for advanced energetic nanomaterials, the idea was that we took an aluminum target, and to overcome that diffusion limited, that oxidation shell, the idea was very simple, that can be coated with something that when it burns, it doesn't form a solid oxide. Carbon burns, it forms our gaseous products, right? So with that, next please, we did this aluminum target with a solvent of toluene and acetone. And the idea, as I said, is forming this graphitic shell on aluminum to prevent the oxidation shell formation, gaseous products, and this shell also hinders porcelain or aggregation. So indeed, when we did that, we found these particles which had aluminum at the core, and you have this carbon shell at the top. Same here, but for the acetone, the first one is for the acetone results, the second one is for toluene. In acetone, we had these amorphous nanoparticles, aluminum at the core and carbon at the shell, graphite carbon shells. And for the toluene, we made these aluminum carbide-like structures, which are crystalline, again coated with the carbon. When we sent these to the Army lab, they tested it using their own technique called laser-induced air shock from energetic materials. We did this with Dr. Jennifer Gottfried, and she was an incredible collaborator. And what we saw was that from the shock velocities that we got, the laser-induced shock velocities, these were the commercial aluminum particles that they were currently using, and these were ours. So the shock velocity had a distinct increase, and the optical power is the net emission from these laser-induced images that they got. And you can see that the two of them had different kinetics. The carbon-coated aluminum had fast kinetics, but net amount of energy was low. But the aluminum carbide-coated carbon had slow kinetics, but had the net, the area underneath the curve, the net energy emitted was a lot more. So we moved on. Now, that was the first step that we did. Now, during this research, we call it serendipity, but the laser, one of the lasers that we were using, the energy went down and literally just had to be repaired. But during that process, we still continued some experiments. And what I found out was a low flux lattice aluminum target and acetone. It started producing these various the intermediate oxides of aluminum, right? So let's look into it. How did we come to that conclusion? When we did the low energy, less than 100 millijoules per pulse, 5 nanosecond pulse with laser ablation with this setup. Next, please. What we got was that we were expecting, still to produce carbon-coated aluminum nanoparticles, maybe of smaller sizes. But when my students came back, they saw all these highly amorphous. I thought it was all dirty things, nothing important, and very low crystallinity, all amorphous. But my students insisted and started looking into it, and we found out that these were some sort of an aluminum oxide, an amorphous aluminum oxide. So far, that's all that we knew. Next, please. The sizes were mostly between 5 to 10 nanometers, so very small sized amorphous particles.
Could you stay closer to the mic?
Oh,
Or-
sorry. Okay. Sorry. And then when we did the EELS electron energy loss spectroscopy, we saw the aluminum age and the oxygen age. They didn't match any of the Al2O3s. Like we tried all the polymorphic phases of Al2O3. It was a unique signature, the black one that you can see there. And when we looked at from the EELS, the elemental composition distribution, At the core, it was like, as you can see, the oxygen to aluminum ratio was around approximately 3, the black line, right? With a carbon shell around it, a thin shell. So far what we conclude was that these were metastable hyperoxidized amorphous aluminum oxide. The X, the stoichiometry was about approximately 3, less than 10 nanometer sizes. We were able to tune in future work, now it's going on, we were able to tune that X, the oxygen to aluminum ratio. And our hypothesis here was that ALO3 was surface stabilized by terminal ALOC bonds, and the oxygen has to be in minus oxidation state, unlike in Al2O3, where the oxygen will be in -2 oxidation state. So this is a very unique metastable oxide of aluminum that was kinetically trapped by the laser during the laser ablation technique. And it also released the trapped gases on solid-solid phase change, which we will show now. Next. So the kinetic entrapment is like, as I described, is like a localized free energy minima trough where the ALOX is trapped while being formed from aluminum and oxygen during the laser ablation process. That's the first energy barrier. And the second energy barrier is when you perturb it, it undergoes solid-solid phase transition to go into theta, gamma, and then finally alpha. But there's still some energy loss from there. There have been only rare sightings of such ALO3. Initially, I was very hesitant to accept from my student, of course. And then we found out that in 1978, there was a single author paper from Sandia National Lab that showed ALO3 stabilization, but in bulk ceramics, vitreous silica. And also in recent years, the Harry Atwater and Korthagen showed that low temperature dusty plasmas also led to such amorphous ALOX with X being close to 3. So we went to Argonne Lashna lab to look at the interfacial structure because we wanted to know how are those bonds arranged and how is it stabilized, such small amorphous particles. We looked at it very carefully with high resolution TM and found out that these were single monolayer of crystalline, highly ordered carbon atoms were coating it like a thin shell on these amorphous particles, which was stabilizing it. Indeed, DFT studies have shown that aluminum oxygen carbon bonds on diamond-like carbon, ordered carbons, can stabilize the aluminum oxygen bonds. So if indeed it's aluminum oxygen carbon bonds, you have to bear in mind that that also supports the fact that the covalent bond dissociation energies for carbon oxygen is about 11.2 electron volts, much higher than the aluminum oxygen ionic bond dissociation energies. So that should stabilize it. So those were our conclusions from here. Moving forward, we did some high temperature XRD analysis to look at this phase transformation process. Initially at room temperature, as I said, there's less than 2% crystalline that shows those little 2 crystalline peaks of aluminum. But as the temperature went up, it became all amorphous. And then it started forming first the gamma theta, the squares symbol, and then the diamond symbols were eventually converting into alpha Al2O3 as also shown in the TM images. When we looked at the crystallite sizes, next please. If you zoom into that zone, then you can see that it forms about the first nucleation around 750 degrees Celsius to 800 degrees Celsius, where it starts forming the first theta or gamma crystals. They're about 3 to 4 nanometers. They grow a little bit, the coarsen, and then they shrink because when it starts forming alpha, it's well known there's a 10% shrinkage between theta, gamma, Al2O3 and alpha Al2O3. So that made sense. Next, please. So the explanation was here's a disproportionation reaction, a solid-solid disproportionation reaction. What's a disproportionation reaction? In which one product goes with one oxidation state is going to 2 different oxidation states, from -1 in ALOX to -2 in Al2O3 and then oxygen in 0 oxidation state. So, and then we have, of course, the carbon burning off as it proceeds. Next, please. So that leads to the permanent trapped gas releases. Unfortunately, this work, I can only present all the detailed physical and chemical characterizations. This has been under classification D from the Office of Undersecretary of the Defense's Office. So the energetic activities, I don't have the data actually to share. But I know that the 2 things that were of value was its high stability. And in some formulations, they were they had good performance. That's all that I know. Anyway, but the thing is that in understanding the fundamentals of such metastable structures is where the beauty is. We wanted to know the chemical kinetics analysis. So we went to regular Arrhenius expressions for deriving the activation energy barrier. We took the XRD data for each temperature cases and we looked at isochronically so that it grows, it crystallizes, it phase transforms in the same time frame at each temperature. And we looked at the conversion rate. Alpha is the fraction transformed or converted into Al2O3, into theta Al2O3. That was our first phase that we are forming. And then using the regular chemical kinetics analysis and determining the KT from the reaction rate constant given by the Arrhenius expression, we found out that of all the models when we fitted it, it didn't go through any of the nucleation models, but it fitted the geometric volume contraction model, which also made sense because my student had actually, I'm not showing it, had actually done a real-time in situ TEM on heating stage. And he showed that the 8 nanometer amorphous particles shrink into 4 to 5 nanometer, just to prove to me that it is volume shrinkage. And so that was an amazing work. And then we extracted from the integral reaction model, the G alpha, you plot it as a function of time. And then you can, for different temperatures, you run each of those and get the slopes and plot it. And from the slope of the temperature as a function of the natural log of, or 1 over temperature, natural log of the reaction rate, we can get the activation energy. What is important is that activation energy barrier is pretty high. For an 8 nanometer amorphous disordered particle, the activation energy is almost close to that of a micron-sized aluminum in terms of stability. So what they found, Army Lab, was fascinating was that this was left for 8 months on disk, and it still activates the same way. So with that, I'll proceed. I'll end my talk here. And the implications of such materials are many. So we are making many such metastable structures. And the implications are that we think of reaction kinetics almost always in terms of temperature. What happens under high pressure chemical reactions is something that we need to think of. That way you can also release energy in the PV term rather than the enthalpy term, right? Which we typically look into the enthalpy term. But if this is indeed an entropically driven, going from disorder to order phase transition, then if it's entropically driven, then the pressure volume term, especially in nanoscale confinements, can have a significant contribution. As you can well imagine, for a 1.2 electron volt jump from that ALOX to L2O3, if we have a volume shrinkage of 2 to 3 nanometers, that's about 10 to the power minus 25 to 26 in meter cube. What should be the pressure, right? A very simple way of looking at it. So I will just end it. Those are the students. I'd like to thank them. They are the fearless warriors. Every day they do it. Ananda and Shubham are now working currently, and they make things happen. Elijah is whose results I presented. Mostly all of that was his PhD. He recently defended. I'd like to acknowledge my collaborators and the funding agencies, Air Force, Navy, and Army, mostly for this project, and the DURIP for transforming this LASIS into a large-scale nanomanufacturing platform. I'd like to just end by saying I'm offering a course. Next slide, please. I'm offering a course. Please, time's running out. Register. It'll be good fun. We'll learn a lot about nanomaterials. Okay, so there you go. Thank you. I have to introduce. Sorry, I forgot. Yeah. Okay, are we ready? So our next speaker is Dr. Daniel Diaz. He's an assistant research professor of aerospace and mechanical engineering at the University of Arizona. And he's going to talk about chemical characterization of aerosols with laser-induced breakdown spectroscopy.
So the laser is working. Okay, so my name is Daniel Diaz. I'm an assistant research professor at the University of Arizona, the Department of Aerospace and Mechanical Engineering. So I'm going to present today the chemical characterizations of aerosols with laser-induced breakdown spectroscopy. So when we talk about aerosols and aerosols analysis, we need to consider two things. The first thing is the characteristics of aerosols. Go ahead. I have a lot of animations, okay? So go ahead. Characteristics of our interest. Okay, so the characteristics of our aerosols are not that fast. Okay. I cannot keep up with that speed. Okay, so multiple origins. Okay, wide chemical composition and wide size range, okay? And now we have to talk about our interest. So we have source location. We want to know where those aerosols are coming from. Go ahead. Speciation, is this elemental, molecular? What type of chemical, results we can get from the analysis? Particle size distribution and concentration density. And we always want to get temporal basis data, right? So we want to know over the time. And so when we observe these two characteristics, when we take into account these observations, characteristics, and interest, we realize that this is a very challenging task. Go ahead. Go ahead. Okay, so what is laser-induced breakdown spectroscopy? So from the beginning from when, let's say the laser was invented, keep going. This was just like the laser-induced plasma was just like a nice observation, right? It took some time for scientists to realize that we can use that spark for chemical analysis. So here we have a spark. Here we have a sensor. That sensor was utilized to analyze high temperature fumes. And probably the most known application for laser-induced breakdown spectroscopy is the NASA rovers currently deployed on Mars for chemical analysis of rocks. So what I'm going to do here is I'm going to present three results, three sets of experiments. The first one is the analysis of contaminated water with metals. The second one, that's at room temperature. The second one is reaction products from combustion processes at 200 Celsius. And the third one is the analysis of gas products from molten salts. All of them are applications for aerosol analysis. So first, let's see a little bit briefly what a laser-induced plasma is and how we can create it. Go ahead. So first, you need a laser pulse. Pulse laser, sorry. So typically, you need the pulse to be 10 nanoseconds or less in duration. You take some optics, and then you focus that beam to a very small spot. Go ahead. So what you want to do is you want a very high energy density in that little region, okay? So the electric field is very high, or you can say that the number density of photons is really, really high. So you will get ionization of the molecules. In this case, if this is air, what you will get is ionization through multiphoton absorption. So then you have some free electrons. The free electrons move in the electric field of the laser, and those free electrons can ionize more neutral atoms through cascade ionization. So this is basically the initial or the onset of the laser-induced plasma. Let's keep going. Okay. So by the end of the laser pulse, this is a diagram that shows time right here, and this is intensity. So this red delta function, let's say, that's the pulse. It represents the laser pulse. So it's about 10 nanoseconds. So at the end of the laser pulse, we have nearly complete dissociations of all molecules, high degree of ionization of atoms, a very high density of charged particles, and the temperature of that gas is very high. They can range between 10,000 to up to 30 or 40,000 kelvins. Now, what we do for us to get LIBS, please go ahead, we need a detector, and then we time the detector. So we need to take pictures of the plasma with respect to this initial pulse, and then go ahead, keep going. So depending on the time that we take the pictures, we can get neutral, ionic, or molecular emissions. In this case, these are ionic and neutral emissions. This is ionic, and these are molecular bands. Keep going. So that's basically laser-induced breakdown spectroscopy. So what do we need for laser-induced breakdown spectroscopy? So first, we need a sample. We can analyze any type of sample. We're interested in this case in aerosols. Then we need a laser. We need some optics, and a spectrometer, and then a detector. So you take the laser beam, some optics, you focus that laser beam. This is a very important distance. This is the focal length of the optical system. Now this can be a few centimeters, can be meters, tens of meters, or even hundreds of meters, right? So, and this is what give us one of the advantage of LIBS, that you can analyze samples at a very large distance. So we create the plasma. This is the light emitted by the plasma. Keep going, the yellow. And then we take that light to a spectrometer and a detector. Now, you don't need anything else to perform LIBS. Here you can have a solid, a liquid, and aerosol, right? In this case, we use a chamber to analyze the aerosol or the gas just to contain it, okay? But you don't really need this, this chamber right here. Go ahead. So let's try to play the left video, on the left. Can you try to play? On the left. Okay, so that's the analysis of a solid. Oh, now it's playing. Okay, and this is the analysis of a gas of an aerosol, right? So, and if we click here, this is the analysis of a solid to create a 2D map. Let's stop it. So that now is the propagation of the shock wave. So the plasma expands so fast that that shock wave is created in the atmosphere, and that's what we hear, okay? Let's keep going. So why do we need LIBS, or why do we think that LIBS is a good technique for aerosols science and technology? So there are several advantages. So real times and in situ analysis, keep going. I have a lot of, okay. We can perform tabletop or remote analysis. We don't need to prepare the sample. We can analyze almost any type of sample. And of course, we can analyze aerosols. So there are two ways to analyze aerosols. The first one is direct analysis, where we fire the laser wherever the aerosol is, right? We don't need chambers, we don't need anything. And then the indirect analysis is that we take the particles, we collect the particles on a filter, and then we take the filter and expose it to the laser, okay? Keep going. Now, there are a few challenges. So first, LIBS needs calibration, but almost any other analytical technique requires calibration. Now, reasonable limits of detection and limits of quantification. In general, the limits of detection of LIBS are, can we please go back, are parts per million, okay? But if you use ICP or mass spectrometry, you can get parts per trillion, okay? Now, matrix effects, all analytical techniques, most of them have matrix effects, so we are okay in that sense. Let's keep going. So now I'm going to present 3 cases, okay? Those are experimental results that we have obtained previously. The first one is the analysis of contaminated water. In this case, we wanted to analyze copper and lead in water, right? So we spike or dope distilled water, and basically we just want to see the limits of detection and concentration, the limits of detection and quantification of those metals in water. Now, we can analyze liquids, but we aerosolize the liquids. So what we did is we put the samples in a nebulizer that you will see next, aerosolize the water, and then keep going, and then we fire the laser in that chamber. So why do we do that? Because we don't want to analyze the liquid. We can do it, but when you perform the analysis on the liquids splash, you create bubbles, so that can contaminate your optics, cool down the plasma, and you don't get the best result. So we aerosolize the liquid, and now we get very good results, actually. Keep going. So this is qualitative analysis, but you can see right here that there is a correlation between the concentration and the intensity. This is the emission line of copper. Next. This is the emission line of lead. And there is a clear correlation between intensity and concentration. Keep going. So when you measure the intensity of those emission lines, you can calibrate your device. This is the calibration created for copper. Let's keep going. The next is the calibration for lead, and analytically is very important to determine the limits of detection and the limits of quantification. So for copper, the limits of detections are 2 parts per billion. The limits of quantification are 5 parts per billion, and for lead are 9 and 28. So those are very good results. If you analyze with atomic absorption spectroscopy, you may get less or better values than this, but because you can do this online in real-time basis, so this is a very good result. Now, the second case is, let's keep going, the analysis of some elements from a battery that failed due to high temperature. So the LEAP setup is basically the same thing, the same laser, the same chamber, but in this case, we put a battery inside in this custom-made chamber. We increased the temperature to about 200 Celsius, and then we waited for the battery to fail. Keep going. So this is qualitative analysis. We obtain signals from carbon, phosphorus, hydrogen, and lithium. You can see here that the continuous line is before the cell failed, no signals, and as soon the battery failed, you can see a very high peak of carbon, phosphorus, hydrogen, and lithium. Let's keep going. So now, if, let's go back, please. When you have these big peaks, let's say, most of the time we're analyzing a continuous media, in this case, gaseous phase. But if we go to the next slide, we will see that some of the signals are not continuous. So for example, here, in this case, we have, I think there are 30 laser shots. Some of them don't show any emission line, but you see that some of them here, like shot number, let's say 1831, you have sodium, you have other. So what is going on, because LEAPS is an intermittent sampling, every time you sample gas, you will see an emission line. But every time you sample, like a gas with an analyte, or your spectra are going to show data. But when you're sampling aerosols, for you to see signals, you will need to sample particles or a conglomerate of particles, right? So here, for example, we didn't see particles, but right here we saw particles. Let's keep going. So that's how we can tell, well, that's one of the ways that we can tell that we have a gas or we have a particle. Now, then we also calibrated our system. In this case, we say that it's semi-quantitative because we assume that the gases released from the battery fail was CO2. There can be other gases, for example, CO, or there can be particles or soot. Anyway, we said most of the gases, and actually it's about 85% of the gases are CO2. We calibrated the system by taking pure CO2, injected that gas to our chamber at various concentrations. These are the calibration points. And then we took the results from the signals from the battery, inserted here, and then we determined that the CO2 concentration is very high. It's actually very high and very dangerous. Let's keep going. The last application is the analysis of gas products from sodium nitrate. So in this case, the temperature, it was 500 Celsius. We built a prototype of a molten salt reactor. In this case, this is the furnace. Right here, let's move on. And right here, we have a crucible. We designed this crucible. This is the diameter is about 2 inches. The height is 2 inches. We put the sample. This is the sample after melting and solidification. So you see that there's some crystal structures. Here you have the melted sample. There is argon going in this direction that pushes all those gas products, and then we perform the analysis here. Let's keep going. So now this is some temporal analysis. So the first experiment was at 330 Celsius. In this plot, you have time in the horizontal axis, LEAPS intensity in this axis, and temperature in this axis. So from 0 to about, I think it's 40 minutes, we don't really have any signal. But when we reach 300, about 310 Celsius, you see some discrete data points. Let's keep going. So here, is when we start detecting signals. Now, at 310, that's the melting point of sodium nitrate. So we're basically spotting the phase change from solid to liquid. Let's keep going. So right here, for example, this data point, this is one spectrum, a very clear sodium emission line. Let's keep going. And then this is another one, really high intensity sodium emission line. Let's go. So now we perform experiments at 500 Celsius. The same plot, this is time, this is intensity, right? So at 300, we start seeing signals. And you see these data points means that we're analyzing either gases or aerosol particles. In these cases, can be little droplets, right? Now, the boiling or decomposition temperature for sodium nitrate is 400 Celsius, and we pass that temperature right here. So that's why we go from 0 to some data points, and then when you decompose, when you boil, it's basically we are boiling. And then because the argon is pushing all that, we are analyzing a bunch of droplets. Now here you can see 37,000 spectra. That means we fire the laser 30,000 times. All these data right here are the spectra that we got. Now, when you have only gas, what you will see is a continuous line of high intensity peaks. But this data point, these discrete data points means that we're analyzing aerosols. Okay, so these three cases are examples of applications of LIPS, and we believe that's why this demonstrates that LIPS is a very good technique for analysis and studies of aerosols in the aerosol science and technology. Let's keep going. So the attendance to this conference was supported by the Department of Defense under that contract. Under that hour, we are analyzing not only aerosols, but we are studying laser propagation in marine and atmosphere conditions. We're performing laser diagnostics, and we're analyzing laser-directed energy. We're studying laser-directed energy. Go ahead. So now I can, if there is any questions, I'll try to address them. Thank you. Oh, okay.
I think, yes, so we have a panel session now, so we are the two channels.
Okay.
No, I think that's yeah, yes, sir, I'm sorry. Not carried away by you.
Great honor.
Okay, that's okay. I'm going to moderate and answer. Please, no problem. Okay. Sorry.
So
Yeah,
it's
please.
a question.
Questions, please. So I'm both a panelist and a moderator. So, yeah, go ahead. Yeah.
Yes. 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 Okay, so. Okay, so the question is, I believe, is basically so those are very, let's say, controlled aerosols, right? So we create the aerosols in laboratory environment. But however, aerosols in the atmosphere, as we saw yesterday, they undergo processes and they become more complex. So the question is, what happens to the limits of detection, right? So first, LIPS is able to do multi-element analysis. In this case, we just have water doped with lead, and then independently water doped with copper. So if we mix them, we will still be able to tell to identify the two of them. When you increase the particle size, maybe your limits of detection are going to change if the particle size is large enough for the plasma not to vaporize the entire particle. Okay, so these are very little particles, I believe if we still have very little particles of the order of 10 microns, and we have similar conditions, the multi-effect or the complexity of the particles may not influence significantly the limits of detection. Now, matrix effects can occur, and the matrix effects is basically the effect, you have your element of interest, but then you have a bunch of other constituents. How those constituents affect your the emission of the specific element. We will have to study it case by case. There can be changes. This is very controlled conditions. I would say maybe they would go between from parts per billion to parts per million. That's a very typical unknown result for this.
Are you saying that matrix could occur even below that particle size threshold where everything can be vaporized?
Yes.
Okay, so matrix effects can occur there, and then that size threshold, you're saying it's 10-ish microns?
Well, it depends on the composition of the particles. Some people say that you can have you can vaporize, fully ablate, and excite particles of 3 microns. Right? So for silica, for example, is 3 microns, but silica is a refractory material. In this case, we have maybe smaller particles. I think and the laser energy was 180 millijoules, which is a big plasma. I think we shouldn't have problems for vaporization of the particles if they are still small. Okay, yeah, but matrix effects are something that will influence a lot the limits of detection. Maybe it will be matrix effect.
Oh, yes.
Cannot hear it very well, so I will put my laptop.
Oh, okay.
Any other questions? Yes, Shruti.
The mechanism is So the question is about the mechanism of different chemicals for the extraction method, especially the zinc chloride and SPT. So zinc chloride and SPT, if we prepare the chemical solution, they have different densities. And the extraction method, we are using density separation method. Plastics have certain density, and nanoplastic may have a little change in density, but probably similar density with other types of the same types of plastic. And those plastics are lighter than the environmental media. And then, of course, the chemical density as well. So chemicals are denser, so lighter plastics will be floated on the top of the solution. So we can just extract the surface water, and then we can do the further analysis. Is that clear? So nanoplastic, okay, so the question is how it can change the nanoplastic. And then I honestly don't have the clear answer for now, even though I have my assumption for the application of those methods. I think nanoplastic can be also extracted because nanoplastic, the size is much lighter and much smaller, and their density probably lighter or similar. So in that case, if we are using the same chemical for the extraction, they will be floated on the top. And then we can extract the nanoplastic as well as microplastic. So it can be possible to use that. But the challenge is not about the extraction method, but challenge is how to collect those nanoplastic using some filtration method. So filtration method may be challenging, and that's why, and also analysis. So that's why it's a little challenging, I said.
Generate metal oxides through the same technique that you described, having alloys.
I didn't get you, like alloys as a substrate and then deposit particles on it? Mm-hmm. Oh, yes, yeah. People have done that to make high entropy alloys. They make the original target an alloy and they ablate it to make high entropy nanoalloys, like nanoparticles of high entropy. Only problem with that is that the two things. One, you have to, which means start with the target where you've already made the alloy. If it's phase segregated in the original target, then your particles will also have phase segregations, right? So that itself is a lot of work. If you have to make already a high entropy alloy metal target. So there are ways we have done up to 3 metal alloy, nanoalloys we have made using lattices. So to overcome that problem, what we did was we took one metal with a very low redox potential, right, as the target. So that's your sacrificial metal nanoparticle that will be formed out of the laser-induced plasma. Once that plasma collapses, those particles will come in contact with the solution. In solution, we put a secondary, tertiary, you can keep on putting quaternary like precursors with matched higher and higher gradient of redox potentials. That way, one will reduce the first one. That will then, it's a chain reaction of redox reactions that you can keep on doing. So I'm taking advantage of the high energy, very small particles that laser ablation produces because of charge screening in the plasma. And those small particles will have very high reactivity. So they'll immediately go and react and do galvanic displacement reactions to produce nanoalloys. We have made up to 3 metal alloys. We are kind of being ambitious, trying to make 5 or 6 metal alloy in the lab now. Is there any other question? Yes. Yeah, Onochi. Mm. Can you be a little louder, please? Well, we want to separate. I don't want to separate it. If it is in aluminum, crystalline aluminum or amorphous aluminum, I'll tell you why. You have an aluminum oxide that is metacic hyperoxide, which holds a lot of oxygen, right? The moment you perturb it, it will release all the oxygen. What will happen if there is an aluminum 10 nanometer particle sitting right next to it? It will oxidize, it will burn, right? So I don't want to separate it out, but because for me, I think it's a single metal format. I'm using the metastability hyperoxide state of aluminum oxide. I have single metal. So what it produces the net, my byproduct will be pure aluminum oxide. Unlike in thermite where you're left with some iron slag, and you have to recycle it, it's a problem. In this case, you have pure aluminum oxide. I can recycle the entire thing and make again aluminum material. Although aluminum oxide, aluminum is quite expensive thing to do. But I'm just saying, so we have single metal product. Now one. Two, I hope that answered your second question. But if you want to separate it, you want to separate aluminum oxides from aluminum in the material, in the product. Yeah. I make these alongside other aluminum oxide. Oh, in the process, it makes some mixes, not pure alloys. Okay, but then can we just talk about it? Do you have any idea, for example, of how you want to separate that? That's a good question because that relates to the plasma chemistry. So now, as Dr. Giaz explained earlier, in the plasma you have all the electrons that are being ionized from the metal to form ions, electrons, then they collide, they form metals collide with the atom collisions will happen, they'll form bimolecular, trimolecular, then molecular emissions will start. If you look at the emissions from the plasma, you can get to see the ionic emissions first. Then you see the atomic emissions in time, then you see molecular emissions in time, right? So from that, one problem with this laser ablation is that right now, unless you know the reaction kinetics in the plasma of what species are birthing and dying in the plasma at what rate, what is the rate kinetics of those species formation and the death of them, you don't know, you cannot predict. Predictably, you cannot say this reaction path will happen. This is literally, it was just kinetically tracked. We still don't have an understanding of how is it tracked. The only way to do that is to do the real-time plasma analysis. Now, that will also tie to your first question. We have a setup now, the Durit that we have from Air Force. We are scaling this entire thing, which was a benchtop lattice when I started it, into a large-scale nano-manufacturing platform. In which case, think about it, what drives every pulse is producing certain number of materials, right? So if I have 10 hertz pulse, instead of that, if I have 200 kilohertz or 400 kilohertz pulse, I can make a lot more materials, and then with tunable energy, beam shaping, all those things that we already do. So that increases the productivity. Second is uniformity of reproducibility of the material. As we said, what if in some batches there are some row edge to it, right, being formed, which is also a disordered aluminum oxide phase. In which case we have to now do what we're doing in this new nanomanufacturing platform. We are setting up a real-time LIBS from underneath the liquid to look at the real-time plasma emissions in time to understand the plasma chemistry. If we don't understand plasma chemistry, then we don't have as much of a control as we have in wet chemistry, in chemical synthesis, where you know the reaction kinetics because you're only making equilibrium products. When you're making non-equilibrium phases, it's like you start a reaction. Imagine if you're doing wet chemistry, you start a reaction and you freeze it after 1 microsecond. Then you can capture one of the metaxylate. Not possible. In the reaction, you get equilibrium. So to understand what will be the distribution of compositions of oxides formation, you have to understand the species birth and species death in the plasma in real time. Yes.
Yeah, thank you very much. I've got two questions. One on macroplastic, another one here. On macroplastic, somewhere you showed that the concentration of your findings in the printing
Laboratory.
you reported it in terms of micrograms per week. So my question is, on a certain area, what's the reference? Was it suspended macroplastic or set with macroplastic? Going forward, you mentioned that you want to assess disclosure risks, scalable or any other program. Or I want to follow up on the question about the LOD and so, for instance, I'm giving just a case if I have like a vapor or smoke from cigarette or electronic cigarette. If can I calibrate the laser with water like we did, and then use the same calibration curve for current type of smoke, for example, will the solvent affect the calibration? So, and also you mentioned that if you change the number of concentration, so it changes the accuracy of the hits. So is there are there thresholds in terms of minimum and maximum number of concentrations that should be considered when measured?
So I will answer to the first question, which is about the microplastic, which I collected from the 3D printing laboratory, what types of plastic I collected. So those plastic sample is fallout sample, so it's not suspended. And I collected a sample for 1 week. That's why my concentration unit is microgram per week. I can divide by days or times, but I don't want to do that because I collected the sample for entire week and some hours. People are not using 3D printer. And then we cannot say this is uniform concentration every day or every hour. So that's why I use the microgram per week. And then that sample, as I mentioned, that is the fallout sample. And because it was the first trial to see the microplastic pollution in the 3D printer laboratory. And our further step, of course, we have to combine both the concentration in the suspended microplastic and also fallout sample because they will have different residence time in the air depending on their density or size. But this is for the fallout sample.
Okay, so about the calibration, I could say that for any analytical technique, the calibration has to be identical. The conditions for the calibration have to be identical for the analysis of your sample. Okay, that applies for atomic emission spectroscopy, that at times for absorption spectroscopy, and this is why. If let's say you have liquid water and then you have alcohol, right? So and then you aerosolize. So aerosol is going to vaporize faster than water. So when you're analyzing those particles, you will have particles of different characteristics. And now we go back to the matrix effects, right? So the particle size is very important. Let's say you have a plasma of 1 millimeter, cubic millimeter. That's your plasma, right? And then you have a particle that is 1/10 of that, right? So the effect or the amount of vaporization, ablation, and emission will depend of that interaction. When you have alcohol, maybe you will have a particle smaller than that. The emission of the analyte is going to be different. Now, that is just the physical matrix effects. Now you will have chemical matrix effects, meaning the alcohol is going to, let's say, have more hydrogen, or is going to have some trace elements. That also affects the emission of the analyte or the element of interest, okay? So you have physical and chemical matrix effects. The calibration has to be done, or the analysis of your samples has to be done in the same conditions as your calibration. Now, also, you have to use the same, in this case, nebulizer for your calibration and for your sample. The nebulizer that we use produces surprisingly very well homogeneous and very reproducible amount of particles. We calibrated, we performed the experiments, and we run the experiments for hours, and it always, with some variance, but it always produced the number of particles and the size of particles in a specific range. If you change the nebulizer, now let's say you're going to have less particles, aerosol particles, or you're going to have larger particles. Now the interaction of the plasma with your particles is going to change. Your emission, analytical emission, is going to change. So the calibration or the analysis of your samples needs to be as close as possible with your calibration. If you don't do that, your calibration may not work.
So here's, I have an interesting question on that, a discussion rather, is that, so it's true that matrix effects are a huge problem in games. That's just been known. So as you said, for your calibration, which means you need to have an identical matrix of the sample,
Yeah.
which is almost always
Impossible.
not possible. It's
Yeah.
almost impossible to have the identical. So it's a big problem in calibration. But actually, LIBS does not need calibration. So we have a bunch of paper in which we have done internal calibration, so calibration free.
Yep.
Thing is that in this case, what you, especially in gas phase, in aerosol phase, if, for example, you have sodium nanoparticles, right? And you have a gas. To control the plasma, we used argon and helium, because otherwise the plasma gets too dense. We used argon and helium. Now the argon and helium is the background, right? So for every pulse that I'm hitting, under the same conditions, same matrix, I can use the argon or helium line in the same window, so that your CCD and the spectrometer has the same quantum efficiency. Those will also affect. The absorption, self-absorption is a problem. Both the lines will suffer self-absorption because they are the same conditions, same time of the plasma, right? The sodium line as well as the background line. Now, if you use Maxwell-Boltzmann equation, then you know emission intensity is related to the number of concentrations. If I normalize the one from the sodium with the one from argon, then I have nullified all the artifacts. It's self-calibration. In which case, we have done this where you have not used any calibration, you've done internal calibration, as we call it. And we got very good results for oxygen content on a 10 nanometer particle, aluminum particle, oxygen 14. So that can be a very creative way of doing it, right?
Yes.
Where you take a background gas and you normalize it with that, because otherwise you have, the transition probability, the weight factors, everything, the energy levels from the NIST atomic spectral database. And the temperature will be equal because they're in local thermodynamic equilibrium.
Yes. Okay. So I agree with you in the sense that we can perform free calibration. I would say that those are ideal conditions. For the real applications, free calibration is very difficult. Like, let's say you have an aerosol, atmospheric aerosol that has multiple elements. And now let's say you're using a Cerny-Tornel spectrometer where the window of observations is 30 nanometers, right? Yes. So now let's say you want to perform free calibration, and then you will need signals from all, in theory, you will need emission lines from all the constituents of the plasma. If you don't have that, your free calibration will be incomplete.
Then it will be a problem.
Yes.
But you can find for each element, if you choose something like argon or nitrogen, that has got many lines
Yes.
on almost every window, right? So in each window, for example, you have 777 nanometers oxygen.
Mhm.
Your 348 nanometers is your, there's an aluminum, 248 nanometers carbon, right? So each of those windows, I can find a subsequent or corresponding argon line existing in that window, if I can.
Mhm.
Sometimes I face the problem where I couldn't.
Yes,
Then it's done.
yeah, yeah. So an
Because
idea,
also, it also depends, as you said, the spectrometer
Yes.
as well as the grating that you're using, right?
Yeah.
1200, 800.
let's say for the aerosols, the water spike with lead and copper, I may be able to do free calibration for the molten salt too. But for the analysis of combustion products, I don't think free calibration is the best technique, because when you analyze these combustion products, you have everything. And you see my windows are very small. I don't know what I'm missing.
And
Ne-
sometimes Eclipse has a few issues, which is,
Mm.
and I know that one of the things that you said is also that sometimes there are specific lines which are affected by self-absorption, others are not.
Yeah,
So the ones
that's
which are
true.
lower to the lower energy state, if it's too low to the lower energy state, they have a lot of like self-absorption effects.
Okay, good. So just to end, so it's true you can do free calibration. That's relatively, it was developed like in the late 90s. So where you take all the emission lines, you perform the Boltzmann plots. However, I didn't consider that just because when you go to more complex applications, you need a lot of information. You need a very wide spectral range. Yeah. Yeah. So we still perform calibration for an analysis. Good. Any other question?
Thank you for your talk, very nice. You touched a little bit characterization it presents of organic matter. How challenging and how did you solve that problem? In my mind, still is challenging. And if you treat or something, you may be changing something in the plastic simultaneously. And how you feel comfortable in doing that.
I think that's a good point. It is challenging because organic matter is one type of interfering the analysis, and also different types of the sample media, like a blood. That is another example. So we have to digest those kind of the organic matter or some different things by using different chemicals. So one of my graduate students is investigating different method, digestion method and extraction method on the physical chemical properties of plastics. So that is the significant challenge, I believe. So we have to sustain the same physical chemical properties of the plastics throughout the whole entire process. And if those properties are changed, then our concentration can be changed because people are using the, for example, pyrolysis GCMS for the quantification of the microplastic or nanoplastic. But that is based on the peak intensity. And then if our chemical composition is changed, then they are changed. So that is the biggest challenging I can say. And another challenge, of course, it's hard to completely remove all of these the things. And what I can do regarding that, I have solution. So the first one is challenging, and then we are still investigating. But second one, this one is possible, because if we are analyzing those samples, organic matter or others, they anyway have different chemical composition compared to the plastics. So plastics, they have distinct the chemical composition, so we can clearly identify and quantify the plastics. But the other one is challenging.
Carrying that to get different peaks compared to the plastic.
Yes.
No overlap.
There are overlapped, but we can extract distinct peaks from the entire chromatography. So that's why I can identify and quantify. But if there are really huge overlap, it's a little hard to interpret the data at once, and we have to spend time more and more to identify. But I think it's pretty possible to solve that problem. But first problem is more challenging, I can say. Thank you.
From now to two will be the benchmark and filter section after information and filter
Yeah, so just a reminder. So we will meet again at 2 for the hands-on instrumentation demo. So we'll meet in this room.
I have 2 slides. Oh, can I just look at my laptop? Oh, okay.
I've saved 1 minute of my discussion time every time by shortening it to minutes. Otherwise, the conference is, I lose back focus hour for 3 minutes. 1.5 minutes is gone in discussing my mind. Right? I decided it's not working. Yeah, sure. They're working on the 20. Now you know why I'm. Now you know what to do. I think also, I think I don't tell you what is going to do. You have no incentive. I think more people. Why are you doing that? Think about it. If I know the structure, I how to show them the class, right? So what you can get in the car. Those are the people that I have here for this that is that if I know all what do I have? I have possibility. Otherwise, I'm blind. Right now, we're blind in itself. You don't know which is the structure. We would like to use our own rapid development. The different labor establishing now this will be heated and this will start getting phenomenal. You start burning the carbon, to net carbon inside. Carbon is a higher energy association than so they have to take some time for the carbon to burn. We can aluminum so now the question is how do you only we can Because this is the unless I know the plasma condition, I don't know the reaction factor. This is happening at very high temperature, 5,000 Kelvin, 110 gigapascal. Sometimes we don't accept it, because this is a very unique area of thing. Okay, very such, so it's a very unique thing that we have. It does form. Sometimes we ignore things. I already had this discussion.
That we have lunch now.
I want to compare the properties, what happens. Now I need to talk to you. I can call you up. It's fine. If you're going somewhere, it's fine. Yeah, no. Okay, sure.
Yeah, so in the afternoon, they will use my computer too. Okay. So
Yeah,
right now
you're
I'm a
going through Zoom, and
participant
then
and then share my. screen.
otherwise I need to click over there.
Okay, yeah.
Mhm.
Okay, that's good.
Complicated.
It's a new facility and,
Yeah.
And it's not working. Previously, they have a microphone system, so no matter
Yeah,
where you speak, it's working.
exactly.
Right now, it's not working.
Yeah, I know, I sent you the.
Oh, yeah.
the PDF.
Sure, great, thank you.
The only problem that I have is the pressure that
And so I won't be there, Yang will be there, you will be there.
You
So,
mean this afternoon?
对, yeah.
For dinner.
dinner.
Oh, dinner, okay.
Yeah. And I don't know where the vegetarian people will sit. So I asked them to divide large dishes, vegetarian dishes to small dishes to serve them.
Okay.
So, and if it's not sufficient, yesterday only 14 people, and today we already have 19 people. And I booked a table for 20, I hope it's sufficient.
Okay.
And if the food is not sufficient, or if the vegetarian food is not sufficient, you can ask them to add.
Okay.
Yeah, it's
We can
totally
ask.
fine. And the minimum is 1,200.
1,200.
Yes, but I only ordered food for like right now, 700.
700?
Yes, last time we have so much left over.
Oh,
So this time I was like, let's do this, and then I didn't order drink, alcohol and dessert. So this actually account for half of the price last year. So this
Okay.
time we do this way.
okay.
So all the dishes are ordered, and then when you are there, you order drinks and
And
dessert if you want.
and add it to the bill.
Yes, add it to the
Okay.
final bill.
Do we pay by credit card or? is it-
No, I already reserved the card there, so
Okay.
they will directly deduct the
Okay.
Julius P card.
Okay, all right,
Yes, so anything happens, just call.
okay, all right.
You'll be fine, yeah,
Okay,
okay.
we'll be fine. Eating, drinking.
Yeah,
Yeah.
yes. I hope the restaurant is okay.
It is a
And
good
I will
one.
be there.
It is a good one,
So
yeah.
they are very responsible, and they are okay to.
All right, hello, everyone. Nice to see you back. So now we're going to start the instrument hands-on demo session. So the way we organize this is from 2 to 2:30, we're going to have these flash talks from all our industrial attendees. So we're going to have 5 presentations in total. So each presentation is around 5 minutes. So after the flash talks, all of us will go to the 4th floor, and then we're going to divide all of you to 4 groups. We're going to rotate among different demos. So each demo is around 30 minutes. So you will also have a student assistant trying to remind you about the time so that we can go through all of the demos. So first we'll start with Netch Group, right? So they will introduce about their instruments.
Okay. Thank you very much, Yang. So I'll give you a quick overview of the Connexus. We talked about rheology and a quick overview of rheology. And so this is the instrument that is here. We also have the capillary rheometer, but it's not easy to ship. So we just brought the rotational, or the rotational belongs to University of Miami. So there are 4 different temperature controllers available for it. One is a Peltier plate that runs from -15 to 200. If you put a chiller bath on it, It can go down to -40. So this is easily removable with the, if I can get this mouse to show, here we are. So on the front here, there's this little handle, you can just slide it to the left. And that lower plate there would actually come right off. So you can easily clean it, you can put it in solvent, it's stainless steel. There's no electronics in it or anything, so you can wash it however you like. If you scratch it, it's easy to replace. And there's also disposable plate options. So if you want to cure a sample, you can actually put a disposable plate on there. We also have a solvent trap cover. So if you're using a sample that dries out, you can just cover it up and stop it evaporating. So that's a good option. Now, if temperature control is really critical, you may want to go for the active hood cartridge. This heats from the top and the bottom. So rather than losing any heat, you know, when you're away from ambient up through the covers and things, you can actually heat from the top and the bottom. And this was kind of computer modeled. You can see on the bottom right here, the modeling, and you can see the resolution, stability, and the temperature gradient. So if you really need to get to 170 degrees and it needs to be exactly plus or minus 0.1, then this is the better option than going for an open hooded plate. Obviously, we can put thermal covers on this, but it's always going to have some loss through the top if it's not heated. So that's up to 200 degrees C, again, -40 with the cartridge, with the chiller bath rather. And then there's the Peltier cylinder. This is for cup and bob work. So if you want to measure low viscosity liquids or use a vein tool or other things like that, you can use this. You can also take out that lower cup and put in a plate insert. We call it a plate insert, and it actually makes it like a flat plate. And so you can use it just like the Peltier plate system. So if you wanted to buy a Peltier cylinder and occasionally use it for plates, you could do that. Obviously, you've got a limited temperature ramping speed and things like that. You can't just ramp up very fast because you're going to be heating up this large block of metal. But if you're doing isothermal work, then it works pretty well between 5 and 90 degrees C. And then there's a high temperature cell. Obviously, people want to use polymer melts and things like that and get to higher temperatures. So we have this, it goes from 5 to 450, and it heats from the top and the bottom. And it actually preheats an inert gas before it comes into the cell. So the sample is heated both by the convective heating with the gas and also with electrical heating from the lower plate and the upper plate, the upper hood. So we've got a combination of convective and conductive heating, which seems to be the best option. It heats up really well without destroying the sample. And also you can cool it with without liquid nitrogen. It just uses a vortex cooling system, and it blows air through the bottom, which is chilled, and that will cool the lower plate. So we don't actually need to expose the sample to air, but it will cool down pretty quickly. And then it's got quite a large gap. You can see here, you can open it right up. You can see in there, it's easy to clean up after you use it. Now you saw the instrument in the first picture. I probably should have said something more about that. So this is the instrument, and these temperature controllers that I was referring to, they fit here into the top as a cartridge. And you just turn this handle 180 degrees and it will eject the cartridge. And you can just take another one and put it in and turn the handle 180 degrees and it inserts it. And it actually connects up all the power, all of the cables, and all of the liquids. So you don't have to do anything. You don't need to be an engineer to use the instrument. It's very good for universities and for multiple user environments where you don't want everybody to have to go through a long training course. You can just clip the geometries in. They're like plug and play, just click it in there and it runs quickly like that. Now there's a lot of different accessories, and it would take me a while to go through them, but I'll just throw them up here on the screen. So UV curing. So if you want to see the curing of something that cures under UV light, solids fixtures for doing torsional tests. You can do it wet versus dry. We've got a solvent trap, as I mentioned, to stop samples drying. A universal container holder. So if you want to clamp a beaker or something like that, you can. Texture analysis tools. That's for doing penetration testing. Twin orbital ball. This is for measuring viscosity of things with large aggregates or big lumps, maybe big stones. Dunoy ring is for measuring surface tension. 5 minutes?
The 5 minutes is finished, so.
Oh, it is?
You need to finish, yeah.
Okay, okay. All right. Sorry.
Just very quickly.
Okay, all right. Well, you can see there's a lot of attachments. I couldn't bring them all here. But if you need to know any more, please let me know. And thanks.
So the rheometer is in a different lab, so it's not on the 3rd floor. So we will need to kind of go, if you're interested in a demo, we'll need to kind of go to the next building, the MEB building. So if you're interested, if you could just let us know. I don't know if you want to show a show of hands if you're interested in seeing the rheometer. Yeah, so there's 1, 2, 3. Okay, 4. So then we can do it at 4:30, right? You were saying?
Yeah, so we can do that lab for, I mean, after we take the group photo, it's gonna be 4:30, and then we can organize a group to your lab.
Group photo is 2:30, right?
4:30.
Oh,
It's gonna be
the
Yes.
lab, okay.
Yes. Thank you. So our next speaker is coming from Marvin Panalytical. Yeah, I think, yes. Sure.
All right, thanks so much again for coordinating the events this week. It's been really fruitful. So I'm just going to give you a quick snapshot of a comparison between the Zetasizer and the Nanosite. You know, the two systems I was discussing yesterday. They're both set up side by side upstairs. And so when you consider, and you know, I received one of those questions, I believe, from one of the gentlemen somewhere here, that was asking, like, you know, why would you pick one versus the other? And so, sorry, this is a PDF, so I'll just do this. So when we talk about the similarities between the two systems, you know, they both look at nanoparticle, you know, sizing analysis. They're, you know, both using light scattering. They both use some variation of the Stokes-Einstein equation. They still, you know, require certain temperature, you know, settings and viscosity. So understanding a little bit about the viscosity of your sample and what temperature you need. You know, they do assume your particles to be spherical. You know, we are looking at hydrodynamic diameter, which again is the spherical equivalent of a particle moving at the same diffusion speed as your particular sample. And then, you know, obviously between the two technologies, there is a whole wide array of publications that have cited the systems. So, you know, any research questions you have, you know, obviously there's someone somewhere has published on it. So, you know, that's kind of the proof in the pudding. And, you know, they're both compact instruments. They're not much larger than like your home microwave. You know, they're not, you know, floor standing systems or anything like that. Pretty easy, pretty quick to use. They're, you know, the analysis for both systems is on the order of a few minutes for each one, obviously depending on how many repetitions you do per sample and so forth. And obviously used in a wide array of research labs and fields of study. So down a little bit more, where they differ. So, and again, this is just kind of some broad strokes on the differences between the two. As far as techniques go, Nanosite uses nanoparticle tracking analysis. We discussed that yesterday. The Zetasizer uses dynamic light scattering. Every once in a while, we have someone that comes up to us and says, oh yeah, I'd like a quote for a Nanosizer. I'm like, okay, is that the Nanosite or the Zetasizer? So just to say that there are two separate techniques, two separate products. Nanosite, you know, NTA will give you high resolution analysis. That means like a 1.2 to 1 resolving power between, you know, peaks. The Zetasizer, for the most part, will be historically a 3 to 1 peak-to-peak resolution. There is a variation of that system that can bring you down to a 2 to 1, and we can talk about that at a later point. Nanosite will give you, NTA will give you a number-based distribution, meaning that if you were looking at a polydispersed sample, you can actually just do number gating, you know, within that population and say what percentage of my population is within a certain size range, what's the concentration within that certain size range, and so forth. The Zetasizer is an intensity-based distribution, meaning you're looking at Gaussian distributions, symmetrical Gaussian distributions of your sample, and you look at the width of that distribution to determine the polydispersity index of your sample. The size range, even though nanosite is a higher resolution technique compared to the other, it has a tighter size range. So depending on your materials and so forth, your limits are about 10 nanometers to about 1,000 nanometers. Historically, we used to actually, spec the nanosite up to 2,000, but we found that the statistics and the reproducibility was just a little bit lacking. So we were ethical in our approach, and said, okay, you know what? Confidently, we're up to 1,000 nanometers. So we brought the spec down. Dynamic light scattering, we can go down to 0.3, 0.6 nanometers. We've had that publication, publications out there showing sucrose and cholesterol down to that range, comparing it to molecular models and saying, yes, we can measure 0.3, 0.6 nanometers. And then on the upper limit, typically it's about 10 microns. However, depending on the configuration and the cuvette choice, you can push that upper limit to 15 or 20 microns, per some data I showed yesterday. Concentration and size dependence, there isn't, it's not dependent with NTA, it is dependent with the Zetasizer. And then the ideal concentration for NTA, you do need to be mindful of your concentration. It needs to be a little bit more dilute when compared to the Zetasizer. Zetasizer, you can work at higher concentrations. Your samples could look a little bit more opaque, a little bit murkier, when you're coming up to the system. But with the nanosite, it does need to be pretty transparent. It can have a tint to it, it can have a color to it, but it should be transparent. And then the sensitivity to aggregates, because nanosite is a number-based distribution, there's a really minimal sensitivity because you're looking at, particles moving around in Brownian motion. So if you've got a large particle, it'll still move around in the presence of a small particle. We're still tracking them independently. So there isn't really any weighting, of the data or the distribution plots to larger particles. The Zetasizer is an intensity-based distribution. So yes, if you do have a large number of aggregates, they might offset the Z average and the weighting of those particles. And then I know Yang's hovering over me. My last line is that, the additional metrics with nanosite is that you have concentration and fluorescence. So high resolution concentration information, fluorescence, you can look at labeling, percent labeling. And then the Zetasizer, the additional metrics would be primarily the zeta potential. There is one iteration out of our 6 different models of the Zetasizer that can do concentration as well. And so if that's a need, you can come up and talk to us.
Thank you.
We also have the SprayTech. Oh, the SprayTech. Yeah, the SprayTech, the laser diffractometer used to measure particle size of aerosols and sprays. So that's also set up there. So that'll be that.
Yeah.
We're right next to each other, so.
Sure. So, yeah, our next speaker is from Aerodyne Research.
Hi, everyone. I'm Anandi Williams here from Aerodyne Research, and today I'll be talking about the different mass spectrometer systems that we sell. But first, I just wanted to put up here kind of the full spectrum of different instruments that we sell at Aerodyne. So we sell both instruments that measure particle phase as well as gas phase. So on the left side, we have 4 different versions of aerosol mass spectrometers that are all kind of equipped for different situations. We have the aerosol mass spectrometer and then 3 different versions of our aerosol chemical speciation monitor. Over on the gas phase side of things, we have our Vocus series, which is a chemical ionization mass spectrometer, which can measure sort of semi-volatiles as well as VOCs. And then 2 laser-based instruments, the TILDAS, which is a laser-based trace gas analyzer that can be configured to measure a range of different trace gases. And then our CAPS instruments, which use cavity attenuated phase shift methods to measure things like NOx and NO. But for this talk, I'll be giving very brief overviews of the different mass specs. So first, we have the aerosol mass spectrometer, also known as the AMS. This was kind of the original instrument that Aerodyne developed back in the 90s. And essentially what it provides is high time resolution measurements of non-refractory aerosol chemical composition, aerosol mass, and the aerosol size distribution. And in addition, it provides quantitative measurements of the aerosol broken down into those 5 categories of non-refractory aerosol. So you get the organics, nitrate, sulfate, ammonium, and chloride masses. The way it works, the way the aerosol is detected is through a 2-step detection process. There's a thermal vaporization of the aerosol particles followed by electron impact ionization. And there is also the option to add in a soot particle or SP module, which enables you to detect some of the refractory components of aerosol, such as black carbon, brown carbon, and a couple of different metals. So here on the right, I have little pictures of the standard sort of HTOF, high-res AMS, and then we also have a long TOF AMS, which has a very long time of flight chamber for increased resolution. In addition, we have what's called the Aerosol Chemical Speciation Monitor, or ACSM. This is the instrument that we brought to show today. So the ACSM is based upon AMS technology, but it's more robust and lower sensitivity, and therefore it's designed for sort of long-term ambient monitoring applications. It uses the exact same sort of detection process of that thermal vaporization followed by electron impact ionization, and also provides real-time measurements of the non-refractory aerosol mass and composition broken down into those 5 components. The biggest difference is its lower time resolution and lower sensitivity, so it has different applications. This is the kind of data that you get out of an ACSM. So there's kind of 2 layers to it. Every 10 minutes or 30 minutes, depending on the type you're using, you get a mass spectrum of the aerosol chemical composition broken down into those 5 chemical components. And then from those mass spectra, we are also able to generate a quantitative time series of the mass concentrations of those 5 species over time as well. A new instrument that was somewhat recently developed is the TOF ACSM with extended resolution, or TOF ACSM-X. So this has the same compact design as an ACSM and is designed for that long-term monitoring application, but it has an order of magnitude higher resolution. So you can see the effect of that higher resolution down here in the bottom right. On the left-hand side, we have a standard TOF ACSM peak shape. You can see we're not able to specifically differentiate between the contributions of different ions that show up at the same mass, whereas with the X, we are able to do that high resolution peak fitting. And as a result of that extended resolution, we have improved organic aerosol speciation, detection limits, source apportionment, and we can get explicit H to C and O to C ratios and oxidation state information. And then a little bit more on the X. So here is kind of also the effect of that high resolution on the organic aerosol mass spectral data that you're able to get. So on the left-hand side, we have an example of a unit mass resolution mass spectrum. We see it's all organics, but we don't have a specific view of what type of organics. On the right, we have that same data processed in high resolution, and you can see it's broken down into different chemical species, different types of organics. And the last mass spec system I'll talk about is our VOCUS series, our chemical ionization mass spectrometers. Got it. These provide real-time measurements of trace gases, aerosols, or atmospheric ions. So I say or because it's very customizable depending on the chemical ionization source you choose. They're interchangeable, and you can use different ionization sources to detect different kinds of compounds, depending on their oxidation state, their volatility. And then we also have different inlet options for the VOCUS. Thank you. Any questions? We can talk at the demo.
Great. Our next speaker is coming from TSI.
Good afternoon. I'm Sherry Elzy. I'm a regional sales manager with TSI. Going to give you a really quick background on the company. TSI was started in 1961 by 5 graduates from the University of Minnesota. Today, we're over 1,200 employees worldwide. Corporate headquarters are still located near the Twin Cities, but we have offices throughout the world, mostly for sales and support. The division that I work in is called Particle Instruments, and that has aerosol measurement techniques in it. So I'm going to very quickly go through generators, counters, and sizers and give you kind of a high-level overview. So we have dry powder generators. This is any type of material that is already in a dry state. You want to take a bulk powder and just get it airborne. And then there are a lot of people who also want to do liquids and suspensions, colloids, that sort of stuff. And so we have a range of generators, depending whether you want to do polydisperse or monodisperse. And then within those subcategories, do you want to focus on the nano range or the super micrometer range? And so there's a variety of generators because you need slightly different techniques, different designs to achieve all of those goals. Then in order to detect the particles, we also have a range of particle counters. Now, I know you probably can't see all the information in this table, but the point really is that there's a lot of parameters that people might care about when they're choosing a particle counter, such as how small a particle can you detect, how high of a concentration can you detect, and so on. And so that's why we have a range of counters. Now, these will just give you total concentration of your particles, no sizing information here. So if you'd also like to know the size as well as the concentration, then we have a range of particle sizers, again, based on what factors might be important for your work. So we have sizers that can look at from hundreds of nanometers up to supermicron range using aerodynamic techniques versus optical techniques. We have kind of a unique device that can give you a real-time mass measurement of PM 2.5 using a first principles technique. And then if you're more focused on the nano range, like below 1 micrometer, we have electrical mobility devices for high resolution, a version that's more portable, and then a version that can do really fast measurements if you're trying to capture data that changes rapidly within 2 or 3 seconds. And you'll see a couple of those in the demonstration upstairs. And then we also have a variety of cascade impactors if you want to collect the material and then be able to do offline chemical analysis. So these don't give you any real-time data output. They just let you size fractionate your material and then do whatever technique you want to do. And I'll just quickly mention a couple new things that we have. These are both part of the demonstration, so I won't go into too much detail because you can learn more. But we have a new platform called OmniTrack. And so it's basically like the size and usability of a cell phone. And then it can connect through Bluetooth to a bunch of different sensor modules. So there's a PM sensor and there's a bunch of different gas sensors. And you can have up to 10 of these sensors all feeding their data into the control platform at the same time. So you can scatter them throughout a facility or throughout different locations. And then we also have a new mini portable water CPC. It's actually dual channel, so it's kind of 2 CPCs in 1 unit. So you can do like upstream, downstream of a filter. You can do indoor, outdoor through a window, or like inside, outside of a mask, and get those measurements at the same time in 1 unit. There's also development underway to make this capable of sending its data also into that OmniTrack platform that I just mentioned. So you can learn more at our website. If you have any questions and we don't get to talk today, please reach out to me or my colleagues, Andrea and Todd, and we'll be happy to follow up with you. Thank you.
So our final talk is about Handix.
Good afternoon, everybody. Today, myself and my friend here, Washim, will be showing you 3 different instruments that we use in our lab from Handix Scientific. So these are basically particle capture devices. And as you know, the particle capture efficiency depends on the size, and it's easier to collect the larger size particles. But what about the smaller size particles? So to collect the smaller size particles, we can learn from nature to amplify these particles. So when you look into various phenomena, like when you go outside on a cold day, you can see your breath and you can see the plume from stack or the cloud formation. All these phenomena, all these activities that you can see, they are based on this principle called condensation. So we can use this principle called condensation to amplify the small size particles to capture them. So the first device that I'm going to talk about is the BioSpot Vivus. So in the BioSpot Vivus, we use this condensation principle. So there is a tube called the growth tube, and basically we maintain different parts of the tube at different temperatures.
So due to this temperature difference, we create a condition called supersaturation. And this supersaturation leads to the condensation of water, drop of water on these particles that we're collecting. For example, SARS-CoV virus. It is usually very small particles, maybe less than 1 micrometer or slightly around that range, or for example, nanoparticles in the air. So we pass through this growth tube and leading to the condensation of water on these particles, and then they can easily be captured. So this device shown here, it has 8 such particle growth tubes, and it's about 2.5 feet high and runs at around 8 LPM to 15 LPM flow rate. We can run at both flow rates. And these particles that I talked about, which are grown using this condensation principle, they can be collected into this Petri dish, a 35 millimeter Petri dish. We can have different kind of media in there, like water, artificial saliva, or even nutrient broth. We can collect these particles into this collection medium. And we can also have cells, lung cells. If you are interested in studying in vitro toxicity, we can have lung cells or any other kinds of cells in this Petri dish. We can grow them in a submerged growth conditions to study the in vitro toxicity. So we can use the same principle, the condensation growth, and mimic the human respiratory system in human respiratory system. And we have the Handic Scientific has also this instrument called DAVID, which is the dosimetric aerosol in vitro inhalation device. So here we use the same principle. The only difference is that in our lungs, the cells do not actually grow in a submerged condition. Rather, part of the cells are exposed to air. So the morphology, the physiology is very much different. So if you want to mimic these actual conditions, you want to make them more physiologically relevant, we use this specialized equipment called the transwells, on which we grow the cells such the part of the cell is exposed to the air. And so the only difference between the Biospart Vivas and David is its more physiological relevance because of this air liquid interface culture wells that we use. So now Washim will talk about the biocascade impactor.
So the last sample that we are using from the Handic is a biocascade impactor. It's a impactor, but the advantage over other impactor is that it can conserve the viability of the microorganism like viruses and bacteria because we collect the sample in a liquid buffer. And the other important aspect of the sampler that it can collect the particle in a size fractionation manner. It has 3 stages in which first stage is collect the particle more than 9 micrometer. In the second stage collects from 9 to 4. And in third stage collects the particle from 4 to 1.4 micrometer, and rest of the things get out from the exhaust, which we can still collect with using a filter and other sampler. So the important part that it collects particle in size fractionation. But why are we interested in the size fractionated particle? Because the size of the particle and droplet tells us how deeper it will penetrate into our lungs. That's how the utility of this sampler is. Thank you so much.
Thank you. So here, I also want to thank our industry attendees for sponsoring our workshop. So without their sponsorship, we cannot have this nice gathering at the University of Miami. Okay. So now let's move to the 3rd floor to go through the actual hands-on demo. So there are 2 elevators here, and there's also a cargo elevator on the other side to fit in this large crowd. And then the student assistants are going to guide you through different demos. And at 4:30, we'll gather downstairs again to take a group picture.